You're all ready to go? Shall we start? Okay. So, again, thank you so very much for being here. It's my first SciPy ever, so I'm absolutely thrilled to be here. My name is Valerio. I'm going to talk about myself in a second. And the topic of today for this morning is privacy preserving machine learning, or machine learning on data you're not allowed to see. Who am I? I have a background in computer science and a PhD in machine learning. I've been working in research for many years, specifically doing machine learning and deep learning for biomedicine. My last appointment was at the University of Bristol, which is where I'm from. But I'm also fellow of the Software Sustainability Institute, and this is one of the institutes I'm representing today. I will be talking about that in a second, because PPML, or Privacy Preserving Machine Learning, is one of the activities tied with my fellowship with the SSI. I'm currently working also as a DevRel in Anaconda, and you might have seen me, probably not with a mask, but I'm actually quite involved in the Python community, especially on the European side. I've been organizing EuroSciPy, which is the European version of this conference, by the way, which is it in Basel? Basel, yeah. We've done the joke many times. And then it's going to be in August, so next month. So if you're interested in, you want to have a quick check on the program, it's right there. It's going to be on the 14th of August. Structure is more or less the same. Today's tutorial, today's conference, and sprints in the end. We also have a maintenance track, so please check it out if you're interested. And, well, that's it about me. What about the aim of this tutorial? I would like to provide an overview of the emerging tools in the Python ecosystem specifically for what is called privacy enhancing technologies, or PETs, with a focus specific on machine learning, because ultimately we're not going to talk about general applications. We're going to try to narrow everything down to the machine learning domain. And so this leads to what is now called privacy preserving machine learning. I don't know why you don't see the slide. Oh, there you go. Sorry. That was what I was talking about. And as we were saying, these activities are linked to, linked to my fellowship plans with the SSI. In particular, my plan for the fellowship was to raise awareness about these technologies, and also some of the effort the open source and the general community, machine learning community is doing on this particular topic. And I found myself working in this topic mostly by chance, but also was very interested, because I always loved the algorithmic side of machine learning and computational side of machine learning. This has a lot to do with dealing with specific computations and cryptography and security sometimes, if you're interested in that. And it's a very interesting joint effort from different communities at the same time. So we have machine learning communities, open source communities, so those developing the tools we're going to talk about today. And so the takeaway message from this slide for me is I would like to gather any possible feedback contribution you have. This is probably the third version, and I'd say the most extended version of the tutorial I've developed so far, but any kind of comment you will have in the end, so by the way, this third version means I have no idea about the timing, so you have to tell me when you want me to stop talking. We can have a break, we can have multiple breaks. I'm actually planning to do that, so feel free to let me know. And oh yeah, there was an award by JGI, which is Data Science Institute from University of Bristol. Anyway, let's introduce privacy. And sorry, this slide's not working. What I'd like to do with this deck of slides is to give you a little bit of an overview very quickly of what we're going to work today together, and then we move on to the notebooks side of things. Why privacy is important, or privacy, if you want, is important. And I'd like to start from analyzing a few key events happened in the last few years. So probably privacy started to gather much more attention from lots of communities when the Facebook Cambridge Analytica scandal was raised to public attention. So we're talking 2014, 2018. In particular, all started from a survey collection of data. Facebook call it a quiz called "This is Your Digital Life," and essentially they invited users to find out their personality type. This was the intention of the survey. But later on, and by the way, the caveat of all that is nothing wrong with collecting data. The problem was that the app collected data also from everything, all the people involved into the public friend list of all the participants in the survey. And later on 2015, The Guardian reported that Cambridge Analytica had this data, acquired this data in some way, and used it to psychologically profile voters in the US, which is essentially, first off, a different use of the data from what was originally intended, but they somehow gathered and acquired this data set and they used it to do that. So we're talking 305,000 people installed the app and 87 million of people gathered, information gathered from these people. In 2018, US and British government lawmakers demanded that Facebook explain how the firm was able to acquire this data without having users' consent. Because, again, it was a different use of what they were initially wanted to do with the data. And so Facebook apologized for the data scandal and announced changes in the privacy setting. That was the beginning of an era, actually. That was changing completely the story of what privacy was perceived as a topic in general when we're dealing with data. What about machine learning and data? Well, first off, we all know, by the way, let me quickly ask you a question. How many of you are familiar with machine learning? I'd say all of you, so perfect, thank you very much. So I'm not going to dive too much into details. What I want to say here is that human learning, as we all know, is different from machine learning. So we do see a picture, but machine learning sees this first off in 3 channels, but most of all sees a collection of numbers. So we all know that machine learning is indeed different from how human learning works. And in fact, we have different challenges in machine learning. So when you have like pictures of apples like that, if you want to train a model to classify apples, you need billions of samples, even for simple tasks like this is an apple, this is not an apple. Whereas we can say, like, with very few shots, very few samples, like this might be apple or not. But what happens when we humans see these apples, these pictures? Are they apples or not? I promise you they are, because according to Google at least, because they're very particular kind of apples, but they do classify as apples. And so this is essentially leading to like a central topic in machine learning, which is, we'll probably know, are very aware. I just want to highlight like a couple of papers over there. That is, when you're dealing with machine learning, ultimately what is more interesting is the data rather than the model. And the takeaway message and why this all is connected to privacy is because at the end of the day, if we would have access to a larger set of data, a more curated set of data, we might be able to deliver better prediction performance from machine learning. But on the other hand, we might be aware that some constraints on accessing these unprecedented size of data can have. And so we have this dilemma. Is it like the more the data, the better the model, but we also need highly curated data sets to have better models. But on the other hand, when we have high sensitive data at stake, we need to keep data safe from both accidental or intentional leakage. So what we're going to try to talk about today is both cases. Like, first off, in the beginning, we'll be starting by saying how difficult might be to anonymize data and what are the challenges there. But also, in the second part probably of the tutorial, is what happens when someone is intentionally sending malicious attack to our data/models in order to steal information. So we try to see both sides of coin here and try to take some messages at the end. So the wrap up of this couple of things here are data and models are normally kept in silos. And what about silos in particular? The reason why I'm saying data and or models is because when you're dealing with like data and machine learning, we normally tend to consider with good riddance we tend to consider the data perspective. And I've been talking a lot about saying data is probably the most important bit in machine learning. And so we need to make sure that privacy guarantees are provided on data. But on the other hand, when you're developing your machine learning technique, your model, whatever, you are also having like some sort of sensitive information there, because your model is your solution, and your solution could be patented, could be subject to like business NDAs and things like that. So it's not just about keeping data safe, but it's also keeping models safe. So what I'm trying to say is we have to keep into consideration both sides of the story here. So it's not just about data, but it's also about models. So what normally happens when you're working with high sensitive data is I do want to have data accounting for privacy. And so what is normally called privacy preserving data or anonymized data, whatever. And in this particular set of, this particular configuration of processing, the privacy is intended as a property of data, meaning that there are techniques, we'll be seeing a few later, talking k-anonymity is probably one of the most popular one. Has any of you heard about k-anonymity before? Okay. It's a quite popular, I'm saying it's popular because I've been working with medical data quite a lot and medical researchers. And when it comes to medical data, normally when you ask for like privacy protected data, what they do is like running k-anonymity. But also, like up to a few years ago, even when you were working with US census data, they were anonymized with k-anonymity techniques. K-anonymity is a very simple technique. What it tried to capture is we tried to work on the data, making sure that it doesn't exist a single row into the database so that that single row can be automatically identifiable, combining all the different information you have in the database. And so the K in the name says you have to make sure that at least K rows in the database are matchable and similar to groups of individuals in the database, so that you're sort of guaranteed that you're not disclosing information about a single individual or a single group of individuals. And so what happens, like whatever, leaving all the details out of this question, is we have a data set with different groups of data, we anonymize it, and then we share the anonymized data. This is how normally these approaches work. So like algorithms can work on anonymized privacy, anonymized data sets, so we're sort of guaranteed that no privacy information is released. But what happens, for example, if we have that data set is a data set of patients' medical records, so the different colors. We do sanitize these medical records. We have the full yellow one, absolutely anonymous. But then we also have another data set. Let's say pharmacy visited. And then we combine these two data sets. Pharmacy visited is some data set we have externally or some data set we may have acquired publicly. We have this data set. We combine the sanitized version of the data set and pharmacy visited. And for example, we can correlate between medical disease and medication, and that's probably the original intention of the data. We want to see what happens. But what if we also we can gather information about patients buying specific medicine from which pharmacy, and then from which pharmacy we can roughly infer the zip code, and so where this pharmacy are located. And so, for example, we can gather the residency of different patients, even without addressing the specific address information. So most visited pharmacy, for example. And so these sort of analyses are not specifically meant to be in the original data set, but if we collect another set of data and we correlate the two, we can have additional information. This is one of the most challenging things. This is why this is a very specific kind of attack. It's called data linking attack, but this is just to showcase how difficult it is to deal with anonymized data set. The two papers here, oh, by the way, I was saying, I mentioned before that US census data was used to apply k-anonymity is not doing that anymore because of some leakage information and like intentional research performed on the data to identify that that data set was not indeed that private. There's also another paper, very interesting one, talking about another case of linking attack on the Netflix price data set, correlating like a fully anonymous movie data set correlated to IMDb. So like this external data set is actually a public available data set. And so what about different solutions? Before talking into that, the question at the end of the previous block was like, okay, nice. So it is difficult to account for privacy in dataset. What about machine learning on all this framework? We've been talking about attacks to the data, but there's also attacks to the machine learning models. We can like have some of them featured in this slide. We have from many years, we have de-anonymization, reconstruction attack, parameter inference attack, model inversion attack, membership inference attack. We've been trying to see a couple of examples here. But so these are all the progress of research in privacy preserving machine learning. And the takeaway message is machine learning applications are prone to different privacy and security threats as well. And in literature, if we have a machine learning model and we assume the model to be a machine learning model as a service, we can have, so assuming that is the perimeter, we can have white box attacks and black box attacks, depending on whether we know how much information do we have about the internals of the machine learning models. So if we know how the model is actually working, how it's implemented, we're talking white box attacks. Otherwise, if we don't have access to the model, but just to the predictions of the model, that is black box attacks. That's the kind of classification we have. Always gathered from like software engineering terminology for testing. And ultimately, the trade-off when we're dealing with utility and privacy is always the same. So it's always a balancing between how much we do account for privacy, but at the same time, how much do we want the data to be useful for the learning process. In other words, if you want in different terms, what I'm saying here is like you can increase your constraints on the data, so accounting to the data, to the privacy of data more and more. But the more you do that, the more you ruin the data originally, and so you're essentially taking away some of the piece of information that were indeed useful for the machine learning model to learn something from it. So it's always a matter of how much privacy I want to disclose, how much privacy guarantees I want, with respect to how much I want the data to be practically useful from the learning perspective. And so, to gather all this information, the kind of a interactive session we'll be having very soon is based on two main approaches. One is data scientist approach. So we try to prefer practical aspects. So we're talking tools and software. We work in the full pipeline as much as we can. But we also have the perspective of the researchers. So we try to have further readings, having a little bit of understanding of what's going on. And also there would be live coding sessions together with you. So let's try to play with it. And I was wondering whether, I don't want to stop right now at this point. Hello, hi. At this set of slides. And we can probably start working with the notebooks. Going to the notebooks, all materials is here on the GitHub repository. If you haven't set up your environment, you can do that. I've just made, and by the way, if you're running on a Mac, as I'm doing with M1 processor, I've been updating the environment like a few hours ago. So like it should be working fine in using M1 devices as well. Is now working? It doesn't? Okay. Yeah. I simplified first and foremost, there was a mistake in my dependencies because I was using the wrong torch vision thing. But if you gather this latest environment, essentially I reduced as much as possible all the packages. And this is going to probably install PyTorch 2.0, which is fine from what we're doing. And but if you're using 1.13, it's similarly fine. And I've have some versions of notebooks also using MPS, so we can work this out together if you like. Fine. Yes, please. Yes. Yeah, that's a very good point, and thank you very much for raising this point. So, full disclosure, we had to have, and by the way, so what's your name, sir? Paul. What Paul was talking about, and thank you very much for doing it, is you have another option. If you don't want to set up anything, you can use Anaconda Notebook service, and because we don't need much GPU in what we're doing, so you can run everything on the notebooks. And I've actually provided ways to open that into Anaconda Notebooks as well. So what I wanted to say is you can go to nb.anaconda.cloud and you'll gather everything there. What we were intentionally supposed to be doing today is like having a specific kernel for SciPy tutorials, but it didn't happen. And I'm like, apologize for that. So my suggestion at this point would be trying to use Py 3.10 and installing a few packages. We're going to miss it. Later today, I'm sure that this IPython kernel will pop up. And so there will be two, I think it's mentioned in the README file as well, in the setup file. The kernel file should be the one with July date. So 2023.07, that's the one. And so if you go to setup and D, yeah, that's the latest one. It was supposed to be another one, which was, that's the one. That's the one that I promise you is going to be probably later today or tomorrow morning at most. So if you want to go back to that. But in the meantime, what I can do and tell to every one of you is if you want to try out Anaconda Notebooks, we have a special code specifically for SciPy, is SciPy 23, which gives you access to starter tier. Anaconda Notebooks works at tier levels. You have 3 tiers, which has been like last week updated to 5 gigabits of space, but you can also have starter tier, which brings you to 10 gigs, PyScript hosting, much more CPU counting, and you can use SciPy 23 code for that if you want to. This is mainly if you don't want to set up anything on your end. So, sorry? They're probably updating the kernels. That's what I do. What I guess they're doing. Oh, yes. Yes. So let's try to linger a little bit and see how that goes. I will check on Slack later. But to be honest, the stack of software we're going to use in this tutorial is pretty standard. So most of it, especially in the first part, is going to be NumPy, Pandas, Matplotlib, and scikit-learn. Nothing particularly special or fancy. And we'll be using PyTorch for machine learning, for deep learning examples. But I believe most of the things could be similarly applied to TensorFlow, if you're familiar with that framework as well. A few mentions of some of the specific packages we're going to use. There are essentially 3. One is Opacus, which is a specialized library in the PyTorch models for differential privacy, which is one of the main topics we're going to talk about today. PHE, which is a partially homomorphic encryption Python library, and Flower, which is a Python federated learning framework, mostly for the last part. Alrighty, so let's good to go. I could probably try to run everything locally for now. So, and yeah, by the way, this is Slack. Yeah, this is probably some mentions about the kernels. Yeah. Anyway, nice. What do I want to do? Let's run a Jupyter notebook. I go notebook or lab. I'm old-fashioned. I prefer notebooks, to be honest. And let's talk about data anonymity. So we start with the first one. Let me zoom a little bit in case you can trust your notebook. And if you're running notebooks, even Anaconda notebooks, if you like to, this like package/theme I've developed. that was my pet project during lockdown. I sort of liked what it was going. So this is not textbook. It's like if you're loving, as I do, tech paper, so tech looking things, that is something that essentially gives you a LaTeX lookalike of your notebooks. And the interesting bit is that when you export this in HTML and you're sharing it, since all the HTML is indeed included after that cell, even if you don't see it, you can essentially share this as a notebook working paper. That's my thing. So, but it's totally optional. It's up to you if you want to use it. All right. So, first thing I want to talk about is references, and the first part of this book, of the tutorial, essentially part 1 and part 2, have been gathered from a wonderful resource I found online. It's called Programming Differential Privacy for Programmers. And it's an interactive book, also featured in a course of data privacy. I don't remember which university, but we can check that out together. This is the book, and this is the original authors. I've been just updating and gathering some of the information. So most of the very detailed informations and further readings are absolutely for part 1 and part 2. I'm totally recommending checking this book out. It's very well done, very well written, and very compelling reading. And it's all based on notebooks, so you can actually work with examples while you're learning. And yes, this is the logo, so implemented there. And I want to get started by clarifying something which is probably not needed. Good morning. Probably not needed, but I'll say either way. We're talking data privacy, and the definition of data privacy is techniques that have the goal of allowing analysts, researchers, scientists to analyze data, learning about trends and sensitive data without revealing information specific to individuals. That's the main goal of data privacy. And just to be clear, sometimes privacy goes hand to hand with security, but security is indeed a different topic. So we might be crossing paths at some point, probably at the very end of the day, with some security integrations, like talking cryptography and very specific kind of cryptography working for machine learning. But for most of the tutorial, we're not going to talk about security as it is. So just to be clear, you can have data privacy without necessarily have security in mind. So it's like two different skills, different expertise. Good. So let's talk about what is indeed a sensitive information within a data set. In the meantime, do you have any question? Doubt? Feel free to interrupt me anytime, by the way. And for those of you coming later, this is the reference to the material. github.com/LarioMaggio, my username, /PPML tutorial. And this is where everything is gathered. So you can find everything there. And let me know if you have problems in accessing materials. Right, so first part of these examples is let's try to work in an actual data set and try to identify what typically refers to personally identifiable information, or also known as PII. We have a data set gathered from census data, to be honest. We have some names, date of birth, social security number, zip, age, working class, some code, education we compare to numbers, marital status, and so on and so forth. We have like census kind of data in this database. And the first thing is, let's try to understand what de-identification means. De-identification is the process of removing personal information into this data set so that this data set is potentially private. Normally, informations like the name, the social security number are private and sensitive information because by definition, they do automatically identify a single individual. And remember, the very goal of data privacy is to avoid identifying single individuals. So let's try to have a very simply de-identified version of the data by removing name and social security number from this data set. And this is what we come up with. Let's imagine now that, and by the way, in general, for any adult into this database, let's say that we have name, social security number, date of birth, and zip code. These are the four columns we're going to talk about and we're referencing as private information in this database. And what we're going to do with this information is like trying to understand how this can be leveraged to de-identify the database. So let's start to give a concrete example of what I was mentioning before, the linking attack. Linking attack, again, is a kind of attack which is starting from a pre-anonymized or de-identified version of the dataset and joining to this version auxiliary data we have gathered somewhere in order to see whether this joint operation can increase the possibility of leaking some information. So imagine that we have our friend's name, Kerry Truslov, some specific information. The auxiliary information that we're going to consider in this particular case are so this is the entry for our friend in the database, just to be clear. So we know that our friend is in the database, but this is just before having any de-identification on the dataset. And the auxiliary information we have, so we play fair and we say, okay, we have some database of date of birth and zip codes. It's a list of date of birth and zip codes. This is what we have. Now try to merge these auxiliary information to the adult de-identified database, merging on date of birth and zip code. So we have an extended version of the database. That's what does pandas merge does. And if we do that, essentially we gathered that there is indeed one single row in this dataset which matches exactly the date of birth we have and the zip code we have. All right. So we essentially running an attack here, very simple, and by gathering this extra piece of information into the analysis, we're able to say, okay, this is exactly the kind of information we're getting. So we don't know whether that is entries of our friend or not, but we certainly know that we know something about some individuals in the dataset. And in the end, it's not really the point of understanding whether that is the genuine Kerry Truslov or not. The thing is trying to get sensitive data out of a de-identified dataset. But at this point, you might wonder, right, but how hard is re-identify Kerry in the original data? So let's say that instead of using both date of birth and zip code, let's try to use only zip code. And if we do that, using merge again, just the zip code, we are essentially able to gather, again, the exact same single row. So zip code is by itself powerful enough to be able to de-identify some information, some sensitive information. And what about date of birth alone? Well, date of birth is like merging multiple rows here. So we have 3 matches. So certainly the takeaway message here is that we know that there is 2/3 the chances that Kerry has an income of less than 50K, which is the actual question we try to gather. And there's 1/3 of chances that Kerry has an income more than 50K. So this is the kind of extra piece of information we can learn from this data set by just merging with date of birth and zip code. So that's good. Do you prefer something more interactive, or do you want me to go through things and explain things? It's really up to you, because I think it's the few of us. So we can decide. You can tell me, stop blabbing, let me play with the code. I'm fine with it. So just let me know if you prefer working more with the code. Probably this part is not that interesting. It's just more getting our bearings into things. So it's not that rocket science in this particular case. But in case, for any reason, you want me to stop and you want to play more with the code, let me know. In the meantime, I'm not going to execute anything, but if you want to execute the code as long as I go through, you're more than happy to do it. So the question at this point is, so we started by asking how is it difficult to re-identify Kerry, but we've seen it's pretty easy. But how much is Kerry special? The question we ask now. And so the first kind of analysis we do is if we do gather unique values, considering only date of birth, what can we say about how selective date of birth is as a private identifier? And we can say that we have some occurrences in the data set here that essentially shows that a majority of date of births occur between, this is an histogram, so we count how many samples fall into particular counts. So we have the vast majority happening between 1, 2, and 3 times in the data set. So meaning that essentially, if we just use date of birth in the full data set, we are able to identify oldest number of people for sure. And so out of, I don't remember, it's like 30,000, we are able to identify 7,000, almost 8,000 of entries, similarly, with no problem, and more than 5,000 with 50% of cases. This is what this plot is telling us right now. So if you want to, you can try investigating the same thing using zip code rather than date of birth and see what we'll get. By the way, there's also a solution here. You can expand if you want. It's particularly easy to do. It's just copy and paste. I just give you a spoiler of what's going to be the considerations afterwards. So situation with zip code, as expected, similar to what we've been doing with Kerry before, is going to be even worse. So zip code is going to be much more selective than date of birth. So I'll do it with you, but I think I have to rerun everything from start. All right, let's do this quick exercise. So I'm going to try to see whether I can use zip code this time. So if we just use zip code, you should be getting something very similar. So if we're using just the zip code, we are in a much worse scenario here. So just using zip code, we're able to identify lots of individuals there. And so it's a very selective kind of information we want to get rid of. That's the essentially take-home message. So let's do some counting and let's see how many people can we actually re-identify. As I was saying, date of birth is quite a selector for possible identities. And so the takeaway from here is just using date of birth, we can uniquely identify almost 7,000 data records, around 32,000. I remember wrongly before it was like 28,000, but it's actually more, it's 32,000. And we can even additionally get more than 10,000 entries here with 50% chances. If we gather both date of birth and zip code in this data set, this is what we get. So it's we are able to uniquely identify everyone in the data set using both date of birth and zip. So the real takeaway message is that here is, I know anonymizing data set is particularly difficult. And the first thing we've been seeing is that combination of different data can be extremely selective. This is the most important takeaway message from this part. And so at this point, something we might want to do, the last check is essentially we are about to identify everyone. We only have like 2 entries having a 50% chances. The other ones are essentially 100% chances of gathering individuals. So at this point, one of the probably most intuitive thing we can do is let's try to find a way to aggregate data. So the idea is if we try to aggregate, like changing the point value with some aggregate version of the value, so synthetically modified so that people go into groups, we can augment the chances of not identifying single individuals, because ultimately that's the goal. So if we take, for example, the mean average of the age in this data set, this is the 38.5 data. But the problem with having gathered statistics on the data set, and it's related to small groups, meaning like if we gather statistics, like we group by education and number, and we gather the mean age for each group, in this particular case, we have different ages. Like this is like just the top 3 in this particular data frame. But the problem is that if we reason at block level, so this was like what the US Census Bureau used to do with gathered statistics, like working at block level. So the statistics were gathered in groups of data rather than on single individuals. But as I was saying, the problem with groups is related to small groups. And there's also another kind of attack, which is called differencing attacks. Differencing attacks is based on a different kind of premise, which is I want to understand whether it is based on leveraging on the fact that we're using statistics there. And the differencing attacks is based on the assumption that if we take out one entry in your database, you might be able to infer whether that entry was originally into the database or not. And the classical example in this case is like we do sum all the ages in the individuals. We're not even counting groups. And if we do gather the sum of all the individuals, and we gather the sum of all the individuals minus the age of the entry we are interested in, we are essentially able to identify exactly the age of the entry we are interested to identify. And even if we had large statistics, we can similarly do the same. So again, here is like we can get exactly that. The age of our specific target is 39 years old. Anyway, the takeaway message here is kind of a recurring theme in data privacy. So releasing data that is useful to make actual analysis is very difficult. Also accounting for privacy. And distinguishing, and this is probably one of the most important things to say, distinguishing whether the intention of the analysis is malicious or not is particularly difficult. So we have to make considerations. This is the real takeaway here. And yeah, the summary is about linking attacks and the identifiable information. So far so good? Any question on this one? All right. Now let's try to make things more interesting, and let's talk about k-anonymity. Right. Okay, k-anonymity is, as I was mentioning, first and foremost, is a formal privacy definition. So it has like a specific definition will be in this part, and the next one will be work around multiple definitions of things. So try to bear with me a little bit. What I want to highlight before diving into the nitty-gritty details is k-anonymity is a formal privacy definition of data. So the definition of k-anonymity says that if we have a dataset D, we can satisfy k-anonymity for a value of k, integer value of k, if for each row R1 in the dataset, there exist at least k-1 other rows in the same dataset, such as the projection of this row, the joint combination of all this row, is essentially the same of Rk. So, in other words, Qi of D is the quality identifier of D, so the private identifiers information, and pi of Qi of D of R represents the columns containing the identifiers. So, as I was saying, the projections of the quality identifiers. In simple terms, the quality identifiers are the name of the columns we are talking about. So one thing we can do on a dataset is checking for a very specific value of k whether that dataset satisfies k-anonymity. Well, is it clear how k-anonymity works? Nice. So what we start with a small dataset, and the reason is I'll explain why we start with this. But and also, by the way, any dataset trivially satisfies k-anonymity of k equals to 1 by definition. All right. So k's always have to be like greater than 1 to be interesting. So let's take this dataset. It's like very hard-coded, nothing really interesting. Just a data frame of like first name, last name, age, pre-test score, post-test score. And we just gather our data set, and we don't care about first name and last name in the end, so we just get rid of age, pre-test score, and post-test score. So the first thing we can do is implementing a very simple function in Python here, which is called isK-anonymized. We pass in a data frame, we pass a value of k, and essentially what we do is we group by for every single column the items of the data frame, and we check that every length of this group is at least k. If that's not the case, this function is returning false, and we're done. Simple as that. So as expected, the data frame is by definition k-anonymized by 1, but it's not k-anonymized by 2 in this case. And, well, the reason is that we don't always have at least 2 rows for each value of the column. So that's pretty straightforward to see. But what can we do in this particular case? Well, the first thing that we normally do on data in order to satisfy k-anonymity is to try to generalize the data. So again, it's like try to gather some information about the data or change information about the data. So like we carefully change some of the values so that the specific information is not present in the database anymore, and so we have clashing. In other words, if we're talking ages, instead of having 24 years old, 42 years old, why don't we take ranges of ages? So we talk about 24 to 40 years old and things like that. So we try to generalize information in the dataset. To generalize that, we implement a very simple function. In particular, we have defts, which is we're just considering numerical types here. And deft, it's going to be a dictionary. For each column, it tells you how much deep you want this generalization to be. And data frame is the actual target. And what we do is like generalizing by power of tens the values in each column represented in defts. So, for example, if we say deft of age equal to 1, we're going to say that we generalize to the upper decimal the value of age in each column, and so on and so forth. So we just get rid of the first name and last name in this case. We just retain the numerical information, and we try to generalize every single value in the database to the upper 10th number. And we gather this particular new data frame. So the generalized version of df is df2, and we have, as you can see, ages like gathered into different groups. So we have 40, 50, 30, and so on and so forth. No problem. So do we check now that df is still k-anonymized by 2? And the answer is still false. And the reason for that is, well, we can try even more. We can try to generalize to a next level. But the problem that is, this is just to identify one particular example, if we keep on generalizing, we keep on removing relevant information in the data set, we end up having none in the end. So this is an example of what I was mentioning before about the trade-off between privacy and utility in the data. This is exactly what it's saying. So this is absolutely private. This is definitely k-anonymized, but of course not at all useful. We can, if you want, try if that is k-anonymized too. It certainly is. All right, so at this point, the question is, does more data improve generalization? The answer is yes, of course, because the reason why it was so difficult to guarantee anonymization into this database is because we had just 5 rows. If we gather more information, is it easier to work with the data set? So let's go back to the same example as before. Let's go back to the census data. And so the whole reason why we wanted to play with this like stupid data set in the beginning was like this important takeaway message. The more data, the better it is for k-anonymity. We again have around 32,000 rows in this database, same as before. We'll consider again the same quasi-identifiers like zip code, age, educational achievement for each individuals. And in this particular case, we just consider a projection of this database for age and educational achievement. We call it age and edu columns. So is the database k-anonymized by 2? No, it's not. So we try to generalize. Let's try to generalize up to the first 1,000 entries. And there will be a reason for that. So we just gather the 1,000 entries, we try to generalize, and still non-k-anonymity, k-anonymized by 2 is not possible. So let's try to understand what's going on. The reason why, even with 1,000 over 5 entries, is still difficult to anonymize with generalization, this database, is because these datasets are indeed outliers. And outliers are the problem of groups, essentially. So if you try to find groups, there will always be some groups that doesn't satisfy the k-anonymity requirement. Like every single group has to be at least k-length. And let's try to remove these outliers then. So in general, the very important thing to say is keep on repeating that anonymizing dataset is indeed complicated. And even if you wanted to find optimal generalization for k-anonymity, that is an NP hard problem. So it's not that straightforward. It's always a matter of trying and always a matter of assuming that you're trying to deal with trial and errors, try to deal with the right sensitive information in your data set. And even afterwards, by the way, after all this effort, if you come up with an external data set, you can run a linking attack and you can waste all your effort in the end. So this is where this whole introductory part is leading. So even if we like understanding how k-anonymity works and everything, we're concluding that, all right, yeah, you can do that, but you have better ways. And that's why I'm like running. But this is like introducing some of the more important topics, or terms at least. In fact, another thing you normally do to deal with outliers is doing clipping. We'll be talking about clipping in general later on. So that's why I want to introduce this term right now. So if we have values beyond some certain thresholds, we can clip them to the upper thresholds and we get rid of the outliers in this way. If we do that, we are even able to try whether the dataset is anonymized up to the value of 7. And in the end, it's not. But what I want to try right now, what I recommend you do, let me try. I should actually remember to execute things so I don't have to go back. What I want to try with you right now is, okay, but what happens if we try different values of k-anonymized? So let's try 2 in this particular case. Still false. So even in this case, I just gathered the first 500 was still not enough. Try if we gather 1,000. No, still not going anywhere. What if we had the whole data set? So what if we had more data? That was one of the main questions we were asking. And if we try with all the 32,000 entries, this projection is still not, by itself, is not k-anonymized. If we try to generalize, finally, and we also, no, we're not dealing with outliers here. We're just generalizing the whole data set. We're finally able to find a k-anonymized version of 2. What is really interesting here is, so if we indeed gather, there's 2 takeaway message here is like, the smallest groups we can get after generalization is indeed 7. So it's 12. I might have probably, yeah, that's my bad. There's an issue in the code. Oh no, sorry. I'm talking 2 different things. The smallest group after generalization of the previous example, which I changed here right now. I changed from 1,000 to from 700 to 1,000. That's why the numbers were not matching. So if we go back to this one, like as it was, 500, apologies, and we try this again, this should be 7. That's it. Well, of course, if we can increase the number of samples, we do have better minimal group size. In the whole data set, we are able to identify k-anonymity up to the level of 21. So the very important say of this last exercise is essentially the value of k you have to choose for k-anonymity is always the smallest of the groups you can gather in your data set. So if you can gather a larger group, that's fine, but still it's always the minimum number of length you can gather from combinations of groups into your dataset. In a whole dataset, we can guarantee, we should be able to guarantee up to K21. So we should probably try that just for fun. So we try 7, and it's true. If we try 21, it's still true. If we try 22, it's going to false, because that's the minimum size. The minimum size of the, the size of the smallest group we can gather in data. Right. So summary of this part, and I think we're perfectly in time, which is quite new for me. K-anonymity is a property of data. This is very important, which ensures each individual blends in within a group. That's the whole gig of K-anonymity. It is computationally expensive because we have to run transformations on the data. In the naive version, we've been doing is like n to the square of the size of the data we have. So the bigger the data, the worse it is. And faster algorithms can take considerable space. K-anonymity can be achieved by modifying a data, calling generalization. And optimal generalization is extremely difficult, and it's an NPR problem, so it's always a matter of trying and see. There is another interesting paper I would recommend. It's called T-closeness, if you're interested in this particular technique. It's called T-closeness beyond K-anonymity. It's a different kind of technique, but it's still based on the idea that privacy is a property of data. What if we try to change perspective at this point? And before moving to section number 2, do you have any questions? Yes, please. Yes, exactly. So it is a very fair question. The thing is, you'll never know for sure. because there can always be data you can gather from outside or from wherever you can gather. That can break your k-anonymity constraint. What k-anonymity can tell you, and that's exactly why I'm keep on focusing on the fact that k-anonymity is based on privacy as a concept of data, is k-anonymity guarantees you that up to a certain number of entries in the database, which you decide is acceptable enough. Because at some point, if you have a database of extremely sensitive information, you cannot guarantee a k value above certain thresholds. So, for example, I cannot guarantee k up to 5 in that dataset. I can say I'm not going to disclose this dataset is impossible for me. All right. So, assuming k-anonymity gives you this guarantee, the only thing it tells you is up to 21 entries are going to be in the smallest group in this dataset. So, up to k equal to 21, I'm absolutely sure that's the minimum size of the group. If I gather external information to this dataset, so I give you this dataset with this sort of contract. It's k21 private. And if you keep on using that and you do your worst on your dataset as it is, there's nothing you can do after 21 entries. But if you just gather external information, not initially considered, that k can go down to a different number. And that's something beyond your constraint. So that's why I'm saying these techniques are tending to be like removed, and the US census is not using k-anonymity anymore because of this. Because we have alternatives, we have better ways to deal with this. And the focus we're shifting to is try to change the game and try to see whether privacy, rather than being a property of data, is more a property of the algorithm working on the data. Is that clear? Where are we going? Okay. So, let's move on to section number 2, which talks about differential privacy. And bear with me in this part because it's going to be full of details. Some of them I'm going to try to explain. Some of them I'm just mentioned. And if you're interested in the very specific details, I'm happy to talk about it later, or like going to the original book, which is indeed absolutely amazing. Just to give you an idea of the path we're taking here, we'll be introducing differential privacy first. Then we're talking properties of differential privacy. We'll be introducing another version of differential privacy called approximate differential privacy. And ultimately, the very goal of this block, it's going to be introducing differential privacy into machine learning. So this is where we're going. Machine learning is our ultimate goal. And just to be absolutely transparent, after that, we're going to finally talk about some threats to machine learning models. So we'll be assuming differential privacy is done, and then we see what can we do there. Right. So what I'm suggesting here is, I don't know if there's any official time for break. So we can take a short break after this one, and maybe after the whole section, and we work together. You let me know whatever works for you. All right, let's start by introducing differential privacy. So, like k-anonymity, differential privacy is indeed a formal notion of privacy. So it's possible to prove that a data release has a property as a privacy property. But unlike k-anonymity, however, differential privacy is a property of the algorithms and not the property of the data. So if you want to prove if a dataset satisfies differential privacy, you have to prove whether the algorithms used to generate the data satisfies differential privacy. And so the formal definition of differential privacy is a function which satisfies differential privacy, by the way, is called a mechanism, or an algorithm, whatever is the synonym, we say that a mechanism F satisfies differential privacy if, for all possible neighboring dataset x and x prime, and all possible output s of the function, the probability of the function to be generating f on x over the probability of the function on x prime to be generating s is less than e to the epsilon. This is the formal definition. Let's try to understand the various components here. First thing, what does it mean neighbors dataset? Simple as that. Two datasets are considered neighbors if they differ in the data by one single individual. That's x and x prime. Yeah, of course. A single entry in the dataset. F is known as the randomized function. And F is typically intended as a probability distribution describing output, not just a single point, meaning that we do have an actual distribution of possible outcomes. It's not just a single value. And the important implication of having this definition of F in particular is that the output will be pretty much the same with or without the data about the single individual. So the entry in the neighbor dataset. So in other words, F, the randomness which is built into F, should be enough so that an observed output from F will not reveal whether X on X prime has been used. I try to rephrase this particular last point in different terms so we can sort of understand what's going on. The whole deal with differential privacy is, imagine I'm giving you a black box, and this black box is what you query. At the end of the day, when you work with privacy, you talk about query to the dataset. So let's clarify this terminology. When you query your data, you're querying f of something. You're querying a function giving you an answer, right? What differential privacy is actually telling us is when you get this answer, if the algorithm generating the answer, but beyond the black box, is differentially private, you won't be able, mathematically guaranteed, you won't be able to tell whether the value you get out from the black box is the genuine original value from the original dataset, or it's a randomized version, noisy version of the dataset. All right, that's the deal. So you ask me what is the number of people having an age less than 40 years old? I can tell you 5, I can tell you 7. You will never know whether 5 or 7 is the right answer. It can be a slightly version of the correct answer, a slightly modified version of the answer. And why I want to do that? So first off is based on the concept of plausible deniability. You will never know whether that specific individual is part of the dataset. And that's the deal with X and X prime. The second is, I'm giving you an answer which is not out of the blue. It's still something very close to the truth, but not the truth, or potentially not the truth, and you will never be able to tell. That's the whole idea of differential privacy. The last bit of the formulation over there is that epsilon, and that's when the interesting things come into play. So the details of everything. So what is this epsilon in the whole of this? It's generally referred to as the privacy budget. So that value of epsilon is your hub in which you tune how much privacy you want when you're generating this answer. So if an adversary can't determine which X or X prime was the input of F, because F again is the oracle, F is what is generating the answer, and you will never know whether this answer was gathered from X or X prime, then the adversary can tell whether the data was present. That was what I was mentioning before. So the epsilon parameter in the definition is called the privacy parameter of privacy budget. And epsilon provides to tune how much privacy, how much amount of privacy you want in the definition. So some value, so the general takeaway here is small values of epsilon gives you high privacy guarantee, large value of epsilon, less privacy guarantees. How we should choose epsilon then? The question is, nobody knows, of course. So it's still an open research question. So there's still lots of work around it. But we do have some rule of thumbs we can apply in the context. The general consensus is epsilon should be around 1 or smaller, and values of epsilon should be above 10. And values of epsilon above 10 probably don't do much to protect privacy. But this rule of thumb could turn out to be very conservative. So it really depends on the data you're using. So far, so good? Okay. So I'm very, very excited because this is very cool. At least to my standards, sorry. So the learning objectives I want to gather at the end of this is define differential privacy, explain the importance of the privacy budget, and use the Laplace mechanism to enforce differential privacy for counting queries. Okay, so now we get into the details, and we try to characterize that function, that f function, what it is really, on one hand, and then we start also talking about querying the database. And the very simple case we consider is then counting, because it's one of the simple things you can do on the dataset, and has very good properties on the dataset, on differential privacy. So the Laplace mechanism is the randomness distribution I was mentioning before. Differential privacy is typically used to answer specific queries, and so let's gather together the same census data and try to answer this query to the dataset, which is again an example of a count query. How many individuals in the dataset are 40 years old or older? That's the query. And the right answer is, so the truth in the oracle is 14,237. If we do introduce some random noise using the Laplace mechanism, and by the way, I'm saying mechanism to be compliant with the differential privacy terminology, or Laplace algorithms is the same thing. So the idea is that our f function generating the answers for our dataset is going to be similar to that. We have f of x, which is lower f of x, which is the original function. And to this output, we do add some carefully selected random noise. So ultimately, so in the counting, so just to be clear on what we're talking about concretely, this value of f of x to the specific lower f of x, with the specific query we've been considering before, so how many people are 40 years old or older, the output of that function is going to be this number, so 40,000 and such. That's going to be lower f of x. And to this value, we're going to add in some additional random noise using the Laplacian mechanism. And this Laplacian mechanism is again based on two parameters. One is the well-known privacy budget we were talking before. And there is another one now parameter in the gig, which is the S, or the sensitivity of the f function. And so lap of S, capital S, denotes sampling using the Laplacian distribution with the center of 0 as k less. That's what we're doing. And S, by the way, is this ratio between sensitivity and the privacy budget. This is the Laplacian mechanism. So what is sensitivity in this function? The sensitivity is what it determines how much the output of the function varies from f or f1 if the input changes by 1. Again, the whole deal about differential privacy is what happens if I have x or x prime, which is neighbor dataset, but one entry. Sensitivity in the Laplacian mechanism tells you how much the value, if you apply the function to the mechanism to two neighbors datasets, how much the value is going to change. And so, let's say immediately one good news in the end, finally. We are considering counting queries. And counting queries always have a sensitivity of 1. Why? Because if we count in a database something, and then we count in a database considering something minus one entry, the value of the counting is going to be the same minus 1. Does that make sense? So sensitivity for counting queries is equal to 1. And that's good news, because this is something we can immediately say whenever we have to do counting, there's no parameter we have to choose, sensitivity can be 1. We only have to choose the privacy budget. Nice. So let's make an example then. So if we do have sensitivity of 1 and an epsilon value of 0.1, the result of the counting query we were doing before, it's going to be this one. So just to be clear, the true counting in the statistics is 14,237. If we do try to apply the lap mechanism multiple times, like 30 times different, or the kind of answer we're going to get all the time is going to be different, but still plausible with the original value, which is this number over here. So as you can see, it's never going to be the right answer, but something close enough. Does that make sense? Brilliant. Now the question is, how much noise is enough? Because you should remember the example of generalization. Same thing, same gig. You can add as much noise as you like, but the more noise you add, the less close to the truth is the answer. And so let's write down this time a malicious counting query in which we specifically asking whether the entry we're interested so much about, this Kerry Truslove, has an income greater than 50k. So if we do gather this query, we know that the shape of this target is indeed 1. Now, the result definitely violates privacy, so because it reveals just one row, there's nothing to say about. But what if we try to apply differential privacy to this malicious counting query? Well, you get this answer. So is it a good answer? Is it a true answer? Well, first, you'll never know whether that's a true answer or not. So, and if we, by the way, try to run, there was a feature, something like run until this end, but that's JupyterLab, I'm sure, yes. Sorry, I want to quickly run everything. Let me do that in a second. Right, yeah. This time is even another one. So, of course, this doesn't make sense because it's not a value for a counting query. You can always return 0, like making a cap. I haven't done that, but you can do that. I try to run this again. Okay, it's 1.25. And anyway, the interesting thing here is like there's too much noise to be able to reliably tell. Which, by the way, is the intended version, the intended goal of differential privacy. You don't know whether that is you're never able to tell whether that's true or not. But certainly, in this particular case, we're adding too much noise to the answer. So it's very, specifically in the beginning, it was 24 something. So it was very, very far from the truth, indeed. Right, this is it for differential privacy. Any question before we dive into properties? Yes, please. Absolutely, yes. Because in this particular case, you're dealing with a counting query. So you know that, and then because you have, remember, you have f or something. So you know this is going to be a counting. And, well, you can do some normalization, but in this case, the real thing is you added too much noise for this particular thing. So differential privacy is actually working as intended, but is not giving, because it's not giving you any, it's not leaking any sensitive information, but it's not really useful information. So we have to tune what we're doing. And that's what we're going to talk about in a second. Sure. Mm-hmm. Yeah. Shall we try that? Shall we try that? We can try that. So, if I understand correctly, what you're saying is, let me gather. So this is my query. Well, that's the query. Let's try to do this example. That's a very good point, actually. Thank you very much for that. So that's the query, and we know that. That's the differential private f. Let's say f is query plus this. Okay. So what we can do is like generating. We want to do min of this is that something? It's still too noisy, but you're not gonna be closer enough to the truth value. But it is indeed a very interesting question, because you can certainly think about how the distribution works, and depending on how much noise you have a more pointy distribution rather than like a broader distribution. And so the chances of like staying close to the truth, it really depends on how much epsilon you're adding to the privacy, essentially. So how much you're scaling your data. In case of counting queries, it's like 1 over epsilon, because it's by definition. And but that's the main point. Yeah. Yeah. Yes. Sure. So if the question is this mechanism, well, essentially you're implementing that as a well, the way I figured is like as a service. So you have something you can query your data, and this data is being returned using differential privacy mechanism. It could be at the level of database, it could be higher level. It really depends on the architecture you're using. Does that answer your question? Okay. There was another question before, but yeah, go ahead. Yeah. Correct. That's very correct. Very correct. You had another question? Or slipped away? That's fine. That's fine. Take your time. No worries. I didn't want to put you on the spot. Sorry? Yes. Yes. Yeah. We can take a break now if you want. So if you don't mind, we can take 5 minutes right now, if that's enough. And it's a very short break, but then we take a long one, I promise. Just because I want to very quickly talk about at least 2 and 3, and then go back to 4, because that's where it gets interesting. All right? Take a break. Enjoy your break. So we convene at 35 past, if that's okay for you. Yes. Yes.
Is it sort of a tongue-in-cheek sort of attribution of maliciousness, or
you'll never know? That's the point.
So I think in cybersecurity we have the
okay.
Attributing a certain anomaly in the system.
Yeah.
The computation that does not satisfy authorization conditions, attributing it to maliciousness is tricky.
Sure.
There's all sorts of finger snaps on the keyboard that result in trying 10,000 times same wrong password.
I see exactly what you mean. Yeah.
Right. So in this case, we say malicious because you can sort of put yourself in the mind of
I believe in the end, when it comes to that, you always assume somebody's trying to break your data because you're trying to get some sensitive information out of the data. So, but regardless of what your intentions are, what we're talking about here is I'm giving you a mechanism or a strategy to deal with whatever is your intention. I'm going to deal with it.
Okay.
So whether that is malicious or not, I'm going to guarantee you absolutely 100% that the answer I give you is...
So we're not in the attribution game.
No. In the protecting game, I would say.
White and black world of designing sort of the...
Very correct.
Okay.
Very correct. No worries. Thank you. Let me quickly see. Yay! We have a new SciPy tutorials environment. So thank you very much publicly, Python Anywhere people. We do have SciPy tutorials environment, so that is the kernel you are recommended to use if you're running everything into Anaconda notebooks. You don't. That's why we set up the environment. In general, you cannot. I tell you exactly what the deal is. Right now, you can't set up your own environment into Anaconda notebooks because storage is going to count up too much. So as the things implemented right now, if you install you can install any package. You can even create your own Conda environment if you want to, but that Conda thing is going to sum up and suck up all your disk usage you have. So the whole deal is we set up an environment for you. In this case, we set up the SciPy tutorials environment, which is an environment that should be comprehensive of all the tutorials Anaconda is delivering at SciPy. So we had everything already installed for you. So for example, and that's something we can try out, and I probably forgot to add the batch for the getting started notebook, but I'm going to show you how I do create batches. So that's another way for me to showcase. Yeah, that should be installed. That's the only one. If you wanted to, you need to install it. Then you can pip install it. That's something you can do, and it's not going to cost you much space, to be honest. So let's, for example, try. Sorry, I'm looking for the get. There's a get ready notebook here. So if we get this URL and we use an application I developed on myscript.com, which is it's in the setup. Sorry. Linked to badge generator. There's a stupid application I developed in mysql.com, which is give you whatever URL you want to in GitHub, and it generates you the opening notebook Anaconda badge. So we can test it quickly. So now this is importing an externally hosted notebook into Anaconda Notebooks. We can select Sci-Fi Tutorials kernel, and if we run this code, we're going to check whether all the dependencies are okay. Lib is okay, NumPy is okay, Pandas is okay. PyTorch is okay, scikit-learn is okay, Sci-Fi Torch Fusion package is okay, Flower is okay, and oh, this is missing. So okay, I need to install it. That's probably my bad. I forgot to include this into the environment. So you can pip install it if you want to, and that works. So it's not gonna cost you much storage. Also, let me just check that Pydantic is. We'll sort it out later. So let's try to check the versions again. I need to restore the kernel, sorry. Restart. The only trouble I see now is that when you import notebooks into Anaconda Notebooks, it gets untitled by default, so it has to be renamed. Oopsie. Start. Right. Start and run all cells. Let's see what happens. I'm sorry. What's going on? Brilliant. That works. Okay. So sorry, that was my mistake. I should modify one notebook, or it's going to affect only one notebook. The PHE notebook was not there. And if you want to use the NotXbook theme on the notebooks, I'm going to show you how that works. So you can pip install it. It's an extra package. I didn't include it in the environment actually. It's really optional. It's to be honest, it's indeed marked as optional here. Where is that? So if you pip install NotXbook theme, this is doing what it does. So as you can see, storage is not going to go up because it's literally a few files. And then you can do something like load ext. I should probably restart. Okay. This is also to showcase that this extension theme I developed is also working in Jupyter Lab, not just Jupyter Notebooks. Because you might be surprised, but if you really get into these things, Jupyter Lab and Jupyter Notebooks have different CSS. And I had time on my hand during lockdown, so I sort of discovered all these things. So it's loadex NotXbook, and then you texify. That's the command, the magic. And there you go. So it changes a bit also the UI, to also the fonts, yeah, using Roman, Latin thing like proper notebook. You can, if you want to, if we're talking about it, it's just like taking 1 minute about this stupid thing. But if you do something like texify ? You access the full options I've developed. So, for example, you can change the font size, you can change the line height, you can change the font size of the notebook, the font size of the Markdown developer, the font size of the code developer. You can change the theme of the Markdown and the code developer. So, for example, also the font family of Markdown. So by default, this is Fira code, but you can use whatever font family you prefer. I think there's a theme like -cdth or like --code theme. A default, I believe, is Material, but you can use GitHub, for example. So, for example, if I say something like Texify --core theme GitHub, it's going to change the theme of the code part. As you can see, the colors are different. And if you go to like not textbook theme, Jupyter theme, there's a GitHub page where you can see the many things you can do. I think I've also popped in like drop caps. That's what I did. So these are the color palettes, font and typeface. Yeah, if you're interested and if you have like suggestions on that particular case, it would be much welcome to this one. Yeah, this is the material type, GitHub theme, whatever it is, crisp light theme. You have different typora theme, Markdown. You have like this HTML for data frames, all these sort of gimmicks. Yeah, that's what I did. I think the real reason why I developed the whole thing as a notebook magic and so extension is if I download this as HTML. No, sorry, I have to export it. If I save the notebook as HTML, for example, it's not working. I have no idea why. Why is it working? Oh, that's interesting. That's a bug. I should report. Well, if I open this one, yeah, that works. So if I export this one into HTML and you open it as HTML, it's going to retain the theme. That's why I wanted to. So you can share this one without installing anything, and the theme is going to be there. So it still looks like a sort of a LaTeX kind of thing. Yeah. Sorry about the digression. Definitely not interesting. Shall we start again? Are you happy with starting again, or break? Brilliant. Right. Now it's when things are starting to get interesting, because so far we've been like scratching the surface and understanding the principles and properties. How differential privacy works. Now let's try to understand a few properties, and this is one of the parts I was mentioning before, that I will be like gathering the very essentials definitions. I'm not going to go much into the details of every of them, otherwise we will be needing 8 more hours and you will be killing me. So it's probably not the point, but you can certainly have a look at the original book with the extensive coding parts. First thing is talking about composition and what you can do. Because now we've been working on a single data set, and we've been having one definition of mechanism, differential privacy, and also one example of queries. So now the question is, what happens if I use different mechanism at the same time with different privacy budget? What happens if I account for multiple queries on the same dataset, or mechanism running on different versions of the dataset? How's differential privacy going to work in this particular case? So the first property we're going to talk about is called sequential composition, meaning if you have 2 different mechanisms, F1, F2, working on the same dataset X, satisfying differential privacy for 2 different budgets, epsilon1, epsilon2, then the mechanism G of X, which is a composition, whatever the composition is, between F1 and F2, which releases a epsilon1 plus epsilon2 differential privacy guarantee. So the sequential composition is vital property of differential privacy because it enables to design algorithms that consult the data more than once. So that's why sequential composition is important. And sequential composition, what it tells you is an upper bound, an estimation of the upper bound of the privacy guarantee that you can possibly have, like using the multiple algorithms on the same dataset. Just to be clear, sequential composition adds up the privacy budget you have in the multiple function and gives you an estimate. It's not the exact value, an estimate of the upper bound of the privacy budget, and so the privacy guarantees you can deliver on a data set, but it's not going to be exact. It's just an estimate, so it can be much lower, but it's not going to be over than the sum of the privacy budgets. That's sequential composition. Parallel composition, on the other hand, and by the way, this is one of the original version of the notebooks. In this case, is showing you the different distributions of Laplacian mechanism using different budgets. So like F1, F2, and F3, which is the sum of it. So it shows you how the multiple distributions compare to each other, and so you can appreciate whether you have indeed different privacy guarantees. Parallel composition is another very important property of differential privacy and can be seen as an alternative to sequential composition. And you will immediately understand where this is going. So parallel composition is considering the same privacy mechanism algorithm, so the same mechanism for differential privacy, applied on what exactly? Applied on versions of partitions of the original dataset X. And when I say partition, I mean disjoint subsets of the data, meaning that whenever you're considering a single individual in the dataset, that's going to be the target only once of the algorithm of the mechanism for differential privacy, because these partitions are disjoint, so each individual is going to appear exactly in one single chunk of data. So formally, if f of x satisfies epsilon differential privacy, and we split a dataset x into k disjoint chunks of data, so that the union of these chunks is going to end up having with the full X database, then the mechanism which releases of the result, f of x1, f of x1k, satisfies still epsilon differential privacy. So note that this is a much better bound because than sequential composition. And since we run fk times, k is the number of chunks of data we have, sequential composition would say that this procedure satisfies k times epsilon differential privacy. Parallel composition says it is indeed an upper bound, but a better upper bound is still epsilon differential privacy. The formal definition matches up with our intuition. If each participant is going to contribute only once into the rows of X, and this row will appear exactly one time in every single chunks, this means that F will only see this particular one time, and so the privacy budget required to work on that particular individual is going to still be epsilon. Histograms are in this particular context, are a very simple example of counting queries on the dataset. And so, for example, if we generate an histogram counting the number of people in the dataset achieving a particular educational level, still considering the census data we've been working with so far, we can run counting queries on the database. And so, for example, each bin in this case is defined by a possible value for a data attribute. So, for example, education equal to high school graduates and stuff like that. It is impossible for a single row to have two values. So this is indeed a partition of the data. And so if we do run an epsilon of 1 and sensitivity of 1, it's a counting query, so we can actually account for sensitivity of 1 using the Laplacian mechanism. We can say that we can apply differential private approaches, and this is our new differentially private database we end up with. So far so good? there is a third property, which is post-processing. I just want to double check whether this is here or not. Should have been here. Anyway, I will check that out later. Okay, now this goes much more into details of sensitivity and clipping, which are the last two important concepts I want to deal with in this block of notebook. First off, sensitivity is talking about Laplacian mechanism, and this is the mechanism which is the reference mechanism whenever we're talking about differential privacy. So the question about sensitivity is, we've been saying that sensitivity is another parameter to choose, and we also said that counting queries have a sensitivity of 1 by definition. But what happens if we have different types of queries? And in particular, we have some kind of summation queries or average queries. And the reason why we're considering this is because those are the main interesting operations, arithmetic operations, we normally perform on data from a machine learning perspective. And also is, and by the way, average query can be reduced as a sum query over a count query. So average is essentially the combination of sum and counting. And that's why we're talking about them. And just like, by the way, when we're talking about parallel, I didn't mention that, but I assumed you already gathered. This parallel composition property from a machine learning perspective is particularly interesting and important because that's exactly what's going to happen when we work on training and test partition, cross-validation partitions using differential privacy. So if we're having this guarantee that applying differential privacy on every single chunk of data, which is disjoint by definition, training and test data, we don't have to change anything in our privacy budget. Epsilon will still be enough for doing the analysis, and that's a fantastic result for machine learning. Right, so talk about sensitivity. Sensitivity is the amount of noise that is essentially controlling. If you remember, Laplacian mechanism is defined in this way, and sensitivity is the numerator of that particular fraction, the particular ratio, and I'm just realizing that this is not doing proper, but it was supposed to be D anyway. Yes. I don't know why it's not working. I will check that later. Sorry. So the for a function f mapping a data from D domain to R numbers, so real numbers, the global sensitivity is defined like this. So the global sensitivity, we have a notion of global sensitivity or local sensitivity. We're not going to talk about local sensitivity because it's going to be too much, but global sensitivity is defined as follows, is the max of the distance between f on x and f on x prime. And so the talking about sensitivity leads to what does it mean to have distance between neighbors data set. And even in this particular case, we can have different definitions of distance. The real thing I really want to highlight in this particular section is we can consider symmetric difference between data sets, which is dx and x prime equal to that particular formula, is that module of the difference and the union between the symmetric difference. But in very short, this is how the distance is defined. So x prime is the neighbor data set. If x prime is constructed from x by adding one single row, then the distance is equal to 1. If the x prime is constructed by removing one row, distance is still 1. If x prime is constructed by modifying the value of one row, the distance is considered equal to 2. So in this definition of symmetric distance between neighbors dataset and global sensitivity, what we're saying is adding or removing entries in the database is accounting as a one single operation, modifying one row is accounting as two operations. there are versions of distance different. The reason why we're considering this particular definition of distance is because this definition of distance results in what is typically referred to as unbounded differential privacy. So you can have different other definition of distance, and so leading to what is called, on the other hand, bounded differential privacy. All of this to say what exactly? So imagine that we want to estimate the sensitivity of a particular function of interest, because this is what we're talking about here. Considering global sensitivity, considering the symmetric distance, we have, let's say, f of x is equal to x. The global sensitivity of f of x equal to x is 1, since we're changing x by changing only f of x by one single value. If we sum x plus x is 2, because we're changing two values. If we're multiplying scalar value 5 times x is essentially changing x by 1 changes, and so changes f of x by 5. And the last thing is the global sensitivity of f of x, which is equal to, so if f of x would produce x times x, this is unbounded, so the change in f of x depends on the value of x. So this is the whole scenario we're considering. And for functions that map data set to real numbers, we can perform similar analysis. And what we're going to do now is essentially considering different kind of queries, and counting queries are the simplest one we can deal with, because we already know that by definition they do have a sensitivity of 1 for the same reason I explained already. So let's say we want to count in the data set how many people are in this data set. So sensitivity of 1 minus the counting of rows where the property is true. So we have 32,561 entries in this database, and that's it. How many people have an educational status above 10? That's the answer. And still considering another counting query. How many people are named Joe Neer? This is 0, so that's it. Nothing to say about counting queries. Those are the easy one to deal with. That's the take-home message. Summation queries, on the other hand, those are very interesting, because summation queries are, they do sum up the attribute values in the database. And so, for example, if we had a query something like, what is the sum of the ages of people with an educational status above 10, we can have a number that. But the sensitivity for this particular kind of query is not as simple as it's for counting queries, because we don't know anything in advance, first of all. It really depends on the content of the values we're considering. And as a rule of thumb, we consider summation queries to have unbounded sensitivity. So when no lower or upper bound exists on the value of attribute being summed. So there's nothing we can say as it is on summation queries. So when we do have a lower and an upper bound, the sensitivity of a summation query is equal to the difference between the upper and the lower bound. But if we don't have a bound, an upper bound on the value when we have a sum, because again it really depends on the content of data we're dealing with, we have another option, and the option is clipping. And that's why the section was called sensitivity and clipping. And before moving to clipping, which is, I promise you, is the last part of this notebook, just mention again something about the average queries, but the real message here is average query can be treated as sum query over counting query. So if we deal with the sensitivity of the sum query at some point, we can, and count query, sensitivity of count query is 1 by definition, we know how to deal with average queries. And the reason why I'm mentioning, just to give you the full picture, I'm mentioning average queries in this particular case, is because we'll be doing a lot of averaging when we train our machine learning models. Yes, please. What is? Yes. Yes. Exactly. That's very true. Yes. But when you're working with sequential operations, you're guaranteed that differential privacy is composable. So you do have property that is still going to work. That's the top message. But that's a very good point. Thank you. Yeah, this is exactly what you anticipated. Fantastic. Nice. So the last thing is talking about clipping, because clipping is going to be a recurring theme here. So we've been introducing the concept of clipping in the beginning when we were talking about k-anonymity as a way to generalize and deal with outliers. And we're sort of doing the same thing in this case too, but with a different kind of context. So the basic idea of clipping is to enforce an upper and a lower bound. This is what clipping means. And so, for example, in your dataset, if you have ages above 125 years old, you want to clip it to be exactly 125. So that you do have an upper bound on the values in your dataset. What all of this has to do with sensitivity, though? Well, the thing is, if you do have some bounds in your data, you can properly select a value for sensitivity, even for summation query. The thing is that, and I do cut the chase here, the thing is you can have a look at the data, see what is the bound of your data, and try to derive a sensitivity value out of this consideration. But this would be a bit cheating and not to say wrong, because you can't select an upper bound and so leading to a sensitivity based on the actual data you have. Because at the end of the day, you will be disclosing sensitive information relating to this upper bound, because this upper bound is driven directly from your data. However, you do have another option. If you do derive your upper bound not from your data directly, but from epsilon differentially private queries you do on your data, well, in that case, you're not disclosing anything. Because the upper bound is not coming directly from any values on the data, but from some perturbed version of the dataset, which is differentially private. So this is all this blubbing and blah, 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 and is leading to determine upper bound with differentially private queries. So assuming that I do have a Laplacian mechanism here to run on my data, and I want to see whether increasing the number of value I consider as an upper bound, how much I can how much the upper bound is going to change as soon as I increase the upper bound of my values into my data. So you can see that the more I go towards 100, and the more is like the value is stabilizing. All right. So something you can say at the end of the day is, considering this particular analysis I'm doing, and by the way, I'm not generating this trend from the actual data. I'm generating this trend from, I'm clipping this data, but this data comes from Laplacian mechanism data. So I'm running multiple times, changing the upper bound of the clip, running multiple times a differential private mechanism here. So once you're dealing with this particular trend, so you are dealing with a trend which is not the actual data, but it's a differential private version of the data, then you can do your consideration. And at the end, you can consider that having an average, having an upper bound of 80 would work in your dataset. Because at some point after this point, more or less the clipping is not going to change much in the result. So you can say, okay, let's clip the values to 80. You will never know whether 80 is an age belonging to the original data or not, because that has been gathered from other differential private analysis. Does that make sense? Did I lost you completely? That was a lot, I know. Is it totally confusing? You can totally say yes, by the way. Is that more or less clear? No? Not really? Okay. Too much technical? Feel free, whatever feedback you have. It's absolutely fine. It's not obvious technical, no. Okay, yeah. You have to, yeah. I do appreciate what you're saying, and I really understand that dealing with this kind of technology can be perceived as daunting, especially in the beginning, because there are lots and lots of details and things like sensitivity, budget, and bounds and upper bounds and queries. So it's a lot to process, I know. So at the end, the real takeaway message we're trying to have here is not, let's put it this way. So is not entirely necessary at this point that you understand every single bits of what's going on. What I'm telling you is that ultimately everything makes sense. So when we apply all of this framework into what we really care about, which is machine learning processing, you will always have like something to go back to saying, right, this is working because of this. And ultimately, this is not entire like random generating numbers because of that property, because of we're doing this particular thing. This is what we're going to. So I'm trying to give you the handles of where you can go back whenever you're trying to make sense of all this. But if you don't absolutely catch all the nitty-gritty details of everything, it's absolutely fine. Okay? And after saying that, I have to just tell you two quick things, but I will be super quick. And I in the interest of time, I'm not going to go much into the very details. I just want to give you I just want to tell you to be aware that there are two things left that we have to deal with, and then we can talk about the interesting things. Well, everything is interesting, but again, it's subjective. It does exist a concept of approximate differential privacy, and the approximation comes from the fact that you don't have one single parameter now, you have a sort of a fallback parameter. You have two budgets you can deal with. But the real apart from the very details, the very interesting bits is approximate differential privacy will have the same properties of standard differential privacy. So you will have sequential properties, parallel composition, and post-processing. And what is changing in the approximate mechanism is instead of using Laplacian mechanism, you're using a different distribution, which is a normal distribution. And why do you want to do that? For a reason I'm telling you in a second. Because so far, we've been dealing with database of real numbers, so function generating numbers. But when we work with machine learning, we're not working with real numbers. We're working with real numbers, if you remember what I told you in the beginning, like, and this is me trying to make sense of things I've said, but it's, if you remember the picture of the dog like leading to matrices of numbers, this is exactly what I was mentioning. And but when you're training machine learning models, you do have vectors. So you're not working in our values, in real values of one single dimension. You work in nk dimension, whatever k is. So you work with vector values. And so this function f, which is the thing we're talking about here, should be working on vector valued data rather than just point data, which is the one we've been considering so far. And so, long story short, first thing is when you're introducing approximate differential privacy, the major drawback is you have an extra parameter, and you're not having an accuracy similar to the Laplacian mechanism. But when you're working with vector-valued functions, and so their sensitiveness, if you remember, sensitivity was about distance, And so when we have vectors, we're going to update our notion of distance. And so when it comes to vectors, what is a notion of distance we can use? Well, we can have L1 norm or L2 norm. This is pretty standard vector value distance. And the long story short is when you have Laplacian mechanism, so standard differential privacy, you can only consider L1 norm in your data. On the other hand, if you have approximate differential privacy, and so Gaussian distribution as a mechanism, you can both consider L1 and L2 distance. So this is the major strength of having Gaussian mechanism and so approximate differential privacy, in which you have a better choice of distance and really depends on what is the distance that makes much more sense in your data. And so approximate differential privacy, long story short, gives you less privacy guarantees but more flexibility in working with data, especially when you're working on back-to-value data, which is the case in machine learning. That's everything really summarized super quickly. And all the details are actually into the notebook. But as you can see in this notebook, there's no code at all. So you'll be more than welcome to read it and tell me if there's nothing that doesn't make sense there. Any question? Okay. The deal is always the same. You can interrupt me anytime. Right. I really wanted to get to this one. As in, trust this. I don't want to see it. Right. Which is differentially private machine learning. All right. So we've been talking a lot about details. We've been talking about properties of differential privacy. What does all of that has to do with machine learning? Well, first off, let's try to define some of the functions we're going to use. Well, we have Laplacian mechanism, we have Gaussian mechanism, and the very difference between these two utility functions is Laplacian mechanism using Laplacian sampling, Gaussian mechanism is normal sampling, and the Gaussian mechanism on vector data, and by the way, they both has in the definition of f function from differential privacy, they both are functions taking two main parameters, s as sensitivity and epsilon as the privacy budget. If it's the Gaussian mechanism, it's going to be approximate privacy, differential privacy, and so you have also delta for the extra parameter. And what is changing here for the vector case? Nothing really, is just the size parameter in NumPy you can pass in. So you can say that rather than like sampling one single value, it samples the number of values. And well, last but not least, we have like zeta clip or g clip to clip values. Probably we're not going to use these functions actually. Nice. So let's talk about finally machine learning. And I'm going to go very quickly about across the details of what machine learning is. I'm just telling you what is the deal with machine learning. We're just going to consider a supervised learning problem. So we have data and we have labels. That's it. And even more so, we're just considering a binary classification problem. So it's going to be 1 minus 1, 0, 0, 1, same thing. Right, so we download the data. Logistic regression is the target model. We do some processing. I go very quickly because we're all familiar with it. If you're not, just let me know. Just generating training samples, test samples. This is what we have on test data, like 9,000 entries. And we run logistic regression from scikit-learn. We train the model on training data, and we test it on test data. So far, so good. So how many samples the model gets correct? We calculate the accuracy, and the accuracy is 82% in this case. So for this data set is pretty decent result. All right, so now let's get into the details of what's going on here. And well, first off, what is a model? We all know what a model is, and in particular, it's a linear model, it's a logistic regression. So, and thanks to scikit-learn APIs, we can indeed have access to the actual values of the models. so also known as the weights in deep learning terminology. So we can have access to the intercept for the model and the model coefficient. So we can probably not take into account the bias term, so the coefficient. Let's focus on the intercept. So we have an array of numbers, and these are the parameters of the model. Now, if we want to re-implement the predict function, not using the library, scikit-learn library function, well, it's very obvious. It's just the sine of the features times the theta coming from the weights, plus the bias, because it's like the decision boundary, and it's a binary classifier, and a linear classifier, so it's indeed an hyperplane separating the two classes. No rocket science here. And in fact, if we use this predict function and we sum and we generate the sum of all the predictions, we've got exactly the same answer of like calculating what is whenever predicted is going to be exactly like the ground truth on test data, we're going to get exactly the same accuracy we got. So now let's do things a little bit more interesting. So we are trying to, at this point, what we're trying to do is like to reinvent the wheel a little bit, which is something that normally we wouldn't do. But I promise you, the reason why we're doing this is just to understand whether differential privacy can be located in the picture of machine learning. So, as you know, scikit-learn has very powerful implementation of gradient descent, different methods. Logistic regression actually works to converge to a solution. What we're doing here is starting to implement a gradient descent function from the very beginning, like starting from the definition of the loss function. And the loss function we consider is the logistic loss, which is what is logistic regression based on. It's a sigmoid function. And this is the logistic loss that we're trying to minimize when we do gradient descent. Are you all familiar with gradient descent optimization? Brilliant. So I'm not going to go much into this there. So you know what's the deal with gradient descent. The idea is finding the gradient and following the opposite direction of the gradient. So we're minimizing the loss function. Nice. So that's what he said. So now the thing is, we can implement a function to compute the gradient. And once we have this function to compute the gradient, we can calculate a single step of the gradient descent. So we have theta starting from zeros, and then we subtract from gradient from theta the gradient of theta and the value of the gradient for the first sample. This is what we get from theta, and of course we can predict on a single sample. -1 is the expected value, -1 is what we predict, so that's good. However, we need to average through the whole samples. So when we do that, normally is we get the value of theta, and then we generate the accuracy considering the values of theta. And this is the 0.75, and this is because we've been running the gradient descent on the full samples, the full set of samples. And that's good progress. We certainly can do better. Now, we need to make two changes to actually get the actual gradient descent algorithm we're all used to. First off, we need to average the gradient through the samples, which we weren't doing it before. That's what I was actually checking. So whenever we calculate a gradient for a single sample, we need to average this gradient through the different samples in the data set, and we return the mean of this value, so it's the average gradient. And this is what we do on the training. And the second problem, like having an iterative approach to converge to an optimum, is like repeating this operation a certain number of times, certain number of epochs in deep learning terms. So now we have a gradient descent function which takes some iteration values, and we repeatedly call the theta update using the average gradient on the full data set. And so this is a very basic implementation of how gradient descent approximation, gradient descent optimization learning works. We run gradient descent a number of times, 10 times, we get this accuracy, which is better. We can try multiple iterations. We can even get closer to the original 82 accuracy, 82% accuracy we had before. We can repeat this operation multiple times, but and probably the other very important thing we have to choose whenever we run gradient descent is making sure that we're not overfitting. So what we're doing here in the last final consideration of reinventing the pieces of machine learning is calculating how the gradient optimization leads to the minimum, either considering the training and the test loss. So we can see that the two losses are so much close, and so we're potentially not leading to any overfitting in this particular case. Nice. So all of this to say, we have been reinventing the beats and bops in machine learning, and we've been like making sure that we're doing things right. This is what we're doing. Now we have to finally introduce differential privacy in this framework. So we're dealing with gradients. So we're dealing with vector-valued data. And one way to make our algorithm differentially private is to add some noise to the gradient itself. So rather than having a training that trains on data based on the actual gradient, we can have an algorithm training on some noise version of the data. And so what we need is have a function that's this time is called noisy gradient descent. And right, we can apply the Gaussian mechanism on vector data. We already have that for the f function for differential privacy. We reuse the average gradient function to calculate the average gradient on all the samples. So what's the deal here? The thing is, for a certain number of iterations, we calculate the average gradient, we perturb this gradient using a differentially private approach or mechanism using the Gaussian approximate differential private, and then we essentially subtract from theta, rather than the actual gradient, the noisy gradient. But the question is, we need for this function to have a sensitivity. And what does it mean, sensitivity for a gradient function? That's the question we need to, the puzzle piece that is missing. And so answering this question is the central difficulty of making the algorithm works, actually. So first is the gradient is a result of an average query, because we know that the grad here is average grad. So remember, now I'm trying to give you like justification of all the multiple pieces I've been telling you so far. We're dealing with an average query. So we know now that the sensitivity of the average query is the sensitivity of the summation query and the sensitivity of a counting query. And some summation query has the problem of being unbound because it really depends, sensitivity at least, because it really depends on the data we're dealing with. So if we want to do that, we need to bound the values of the gradient. So we go to something which is called gradient clipping. Gradient clipping is applying clipping strategy on the values of the gradient. And if we want to do clipping, we need to have a distance because it's still sensitivity. And how do we do that? We use the L2 sensitivity norm to do gradient clipping. This is just to, again, give you reference to the different pieces I've been telling you so far. So let's say that we define a function called L2 clip this time. We have the norm of V, which is going to be the gradient vector, and we're going to do order 2 for clipping. So it's going to be L2 norm, and if the norm is greater than B, we can return this one, otherwise we return B directly. So either we scale it or we return B directly. So now that we have an actual framework to deal with sensitivity, so it's an average query, so we have to deal with summation, and so we need a concept of distance, like summarizing again. And so we have L2 clip as a way to clipping gradient values using L2 norm. And we can use L2 norm, by the way, because we're using Gaussian mechanism. So we can use either L2 or L1. And so gathering everything together, we can have the query to sum over the gradient, as in the new gradients are going to be the L2 clip whenever that is needed. B, by the way, is the upper bound. And so we calculate the gradient of theta, xy, and yi. We clip the value if needed, and we repeat this operation for every single sample in the dataset. These are how the gradients are being generated now. And then we sum this L2 clipped gradients. And this is dealing with the summation part of the average. What about the counting part? Well, the counting part is easy because it's a counting query. We don't have to use approximate differential privacy at all. We can use Laplacian mechanism directly because it's a counting query. So ultimately, whatever previously was a single line, and I want to compare the two pieces of code. So before, it was like this one. Gradient is equal to average gradient. But now we're doing things with differential privacy. And so with sensitivity definition. So this time, we can say that sensitivity can be any number, let's say 5. And we are replacing the average gradient as in the differentially private sum of the gradient, the differentially private noisy count, and which is the differentially private count query, and then the noisy average gradient this time is the sum, the noisy gradient sum over the noisy count. And this comes from Gaussian mechanism vector applied to the gradient sum, clipped value. So that's good. Is it too quick? And anyway, so assuming that this is working, let's try, this is correct, let's try to run it. And if we run it with like having 10 is the number of iterations, epsilon is the privacy budget, 10 to the minus 5 is the delta for the approximate using in the Gaussian mechanism, we get an accuracy of 0.77. Still not 0.82, but this time we're absolutely sure that nothing is going to happen if we gather data in a non-differential private. For now, believe me that this has an ultimate goal. I will demonstrate this goal in the next block. The real takeaway message here is if we perform k number of iterations, then the sequential composition satisfies. And so the algorithm is not only satisfying epsilon delta differential privacy, but satisfies k times delta plus epsilon and k times delta plus delta differential privacy. Right, so the very last thing to say, to giving you the full picture of how things really working in detail, whenever you have a differentially private grade descent algorithm, is you can perform you can use differential private on gradients. However, you have a better option. Rather than working directly on the gradients, why don't you work with the data, the training data? You have two options. You have two advantages of doing that. Computation is going to be easier, and you do apply these operations only once because you sort of apply differential privacy algorithms on the data once, and then you run your grade descent algorithm, whatever. Okay? So the last section in the notebook is, rather than clipping gradient descent gradient value, why don't you clip training data instead? And you can do that, and you can do that only depending on the specific loss function you're considering. Because the loss function we are dealing with, the logistic function, as a property, which I'm looking for, which is this one. There you go. Is the Lipschitz continuous. But so essentially is thanks to this particular property, the logistic loss function has, we can also say that so this particular property allows us to say that we can clip the values of the training samples instead of the output of the gradient function, and so we can obtain a reasonably valid L2 sensitivity of the gradient. But the real truth is, so it is computationally more efficient, but many useful loss functions used in deep learning specifically are not do not have a global bounded sensitivity. So at the end of the day, we can clip the training samples, but training the gradient values is computationally less efficient, but generally safer to apply to the data. Nonetheless, this last part of the notebook is essentially demonstrating you how to clip the values of the training samples rather than the gradient values. The very difference is that we've been moving the clipping operation like out of the for loop, so it's going to be applied only once, and so we can similarly rerun all the gradient functions here, this time with no L2 clipping because the data has been clipped already outside, so we don't have to clip the gradient again. Yes, this is the real apart from the very details. This is probably the interesting part, because this is justifying the always final conclusion when you deal with any privacy mechanism on data. And it's about the trade-off. So how much privacy guarantee you want to apply on the data, and how much these privacy guarantees are going to affect your final accuracy. So this chart here is essentially trying multiple versions of multiple values of the epsilon, so privacy budget on the data, and it's producing the accuracy. So we try, so remember, the smaller the budget, the higher the privacy guarantees. So you can see that we can indeed apply a very small budget and have high privacy guarantees, but a very poor accuracy. So we start from 0.74, and we reduce the number of privacy guarantees by increasing the budget, and we improve the performance. So it's always, again, a trade-off. So what do we want? More utility or more privacy guarantees? And the question is always a trade-off. But this is just demonstrating that particular point. And so, like, moving from 0.0 to 0.1, I'd say, accuracy was pretty bad until at some point we start improving. So probably a good value for a privacy budget in this particular data set is 0.04. That's the take-home message. Does that make sense? Yes. Okay. Yes. No worries. We're going to see right now, like after the break, because I need a break now as well, an example of how this mechanism used during training can be effectively used in inference. I spilled the bean. After the break, we're going to go back to the presentation. And so this first part was to give you the framework. Now we go and we talk about the actual cases. And if we go back to the examples, I do probably close the presentation, so I think I have to restart it, sorry. So we will here model threats. So we go back to the threats, and we try to understand some vulnerabilities. Adversarial example is very popular, but it's not going to be, it's just to talk about vulnerabilities, not going to have anything to do with differential privacy. This has instead model stealing, and in this particular example we'll be seeing model inversion attacks. So the model inversion attack is what you're looking at on the right hand side of the picture is the original data, the left hand side of the picture is the reconstructed data from the trained model. What I'm promising you at the end is if we do train the same machine learning model using differential privacy, you will not be able to reconstruct any data whatsoever. And that's where we go. And we will see it working, so I'm pretty sure it's going to work. Any other question? I'm sorry for the very lots of details in the first part, and thank you very much for bearing with me. But the second part is going to be much more interactive, I promise you. Shall we take a break now? Like, I would say 20 minutes, half an hour, whatever works for you. So if we restart at 11, I think I can do whatever is missing up until the end. Let's do that, all right? Good. In the meantime, I will be here. Just need to grab a coffee or something, and then I'll be more than happy to take any questions or doubts if you have it in the meantime. And in case you were not here before, now you should be able to run everything on Anaconda notebooks. So it will be, you can go to the repository, and if you want to, and in the README file, every single notebook should have their own specific badges to open directly into that. So like this one, you can open. Membership inference attack is what we're going to talk about later. You have to select the SciPy tutorials kernel because it's the one having all the packages. Sometimes you need to uncomment some of the lines because I need some external modules. So you need to download them from GitHub, and you can essentially do this directly like that. And then, by the way, this notebooks thing is optional, so don't worry about it if that doesn't work. So it's simple as that. I do uncomment this one, and I run it. So I'm getting this. There you go. Because this is the library functions I'm going to take, but I've written this, so you're more than happy to have a look at it. Right, let's have a break now. And we reconvene in 22 minutes at 11. Good. All right. So thank you very much for not running away yet. And let's talk now to the second part. Model threats. So now we sort of assuming that we do have all the building blocks we need to put everything together, but I slightly want to do a very small step back on model threats, model attacks, and when and how things can possibly go wrong with machine learning models. So the first is talking about a very popular example, introducing adversarial examples. This is a very popular case in which we do have, and the reason why we're talking here, this example, is it's a specific kind of attack which still goes into the black box attack because we're not dealing with data. Model internals. I was pausing for a second just to be sure that I was saying the right thing. But this kind of attack works on data level. So the idea of adversarial example is, let's tamper the data we pass into the model in a way that they do look genuine to a human eye. So if we compare the two panda pictures from the left and the right hand side, you will probably say they're both the same picture, but indeed they're not. And this carefully chosen noise we had to the data, it's selected in a way that the model will be fooled in producing the wrong prediction. In other words, we start from a picture on the left-hand side, and that the model says it's a panda with 50.7% of confidence. We add to this picture some noise, carefully selected using the sign of the gradient, which, by the way, is the opposite of how the model works, because the model optimizes in the inverse of the negative sign of the gradient. We're adding something that goes in the opposite direction of the gradient, and the new image is going to look like a genuine one, but actually it's not. And the produced prediction after the model is, this is a picture of a gibbon, 99.3%. And this is the idea of model vulnerability. So we'll be seeing an example of that. Another interesting case of model attack is called model stealing. And we'll be considering this family of attacks called model inversion attacks. The idea of the model inversion attacks is a black box kind of attack to models. And what you're looking at, as I said before, on the left-hand side, you see the recovered image you can get out of the model, and the right-hand side corresponds to the actual training image used into the training of the model. So the whole idea of the model stealing attack is that you are using the model as a black box predictor. So you're sending queries to the model so that you gather the result from the model and you work on these results in a way that you keep on asking predictions to the model, passing in different input data, so you want to gather better prediction, with the idea that ultimately the model will release some information that are actually embedded into the weights of the model. And the whole takeaway message, the whole point of model stealing attack is models do suffer from a sort of an issue of memoization, meaning that whenever you train a model on some data, the model is going to contain this information into their parameter. Now, if we're talking faces, it's going to be an interesting example, but no harm done, really. But if we're talking medical data, medical imaging, when certainly you have a highly sensitive data case, well, if you're able to steal the original data set, whatever quality of this data is, but still, you can reconstruct some data that the model has been using during the training, well, that's a high privacy risk. And that's what we're trying to avoid. And so how differential privacy is going to fit into the whole thing? Well, again, differential privacy starts from this particular concept. In this particular data set here, I do find this example particularly clarifying. In this particular case, we're having a data set of pictures here. And if we look at every single picture, we can see all the single details. So we can see really what are the faces, what are the people included in this data set. But what we're really interested in when we work with this data set from a machine learning perspective is the bigger picture. We are actually interested in the very teeny tiny details of the single item, the single sample. We are interested in the training samples, not the single sample. But nonetheless, the single sample is there. But what if we, instead of considering this version of the data set, we do consider a noisy version of this data set, so that the single information about the individuals is not going to be reconstructible, but the bigger picture still remains. That's the one. So this is the whole idea of differential privacy. I should have probably do this way before, but in the end, this is what we're going to. And well, this is differential privacy. The specific framework we're going to introduce is Opacus. It's a wonderful project. And Opacus is indeed a differential privacy engine integrating into PyTorch differentially private algorithms to train your model. And there's a video clip which explains how the training of the deep learning network is going to work. So normally in the forward step, you have the weights change from left to right, and then you have a step back updating the weights on the loss values. If you're using Opacus and so differentially private, what we're doing is when we propagate back, we use gradient clipping on the layers, then we aggregate and we pass in some noise, which is Laplacian mechanism or Gaussian mechanism, exactly the same thing we'll be talking about. And so ultimately the model is going to be trained containing sensitive data, but still anonymized, protected by differential privacy. So at the end, what we're trying to achieve is when we try to reconstruct data from a differentially private trained machine learning, deep learning network, we're not going to steal any information. This is what we're trying to do. This is the last part. So let's go to the notebooks. And so the first thing I'm going to go very quickly is the fast gradient method attack. And I just want to show you what's going on. We're gonna consider this is the example I took in the slide. Let's talk about the MNIST dataset very quickly, and we're gonna start using a LeNet, which is a very popular convolutional neural network working on images. And the dataset we consider is the MNIST dataset, so the digits, the handwritten digits dataset. The model is pre-trained, so you don't have to run the training. We'll be using all the model only in testing inference, and these are the tiny bits of things I've added in order for you, if you're having M1 chips, to run it on MPS using PyTorch optimization. So this is to download the weights in case you were running on Anaconda notebooks. And so we have a pre-trained model. We have 2 convolutional networks, drop out 2 linear layers, that's it. So MNIST dataset, and before the attack, I'm not going to run it, but before the attack, we do have 98%, 0.98 accuracy. So the model is actually working on MNIST dataset. What if we do run the attack now? No, the attack works this way. We take an input, an image, which is a torch tensor. We have an epsilon, which is the amount of noise we want to add to this image. Not to be confused with the epsilon of the privacy budget. It's a different epsilon. It's a noise epsilon in this case. And then we have the data gradient. So we calculate the gradient of the actual data. First is we take the sign of the gradient. We change the original data by summing up to the image a quantity, which is the sign of the gradient, times epsilon, which is controlling how much noise we're adding. And then we clip the value between 0 and 1, because it's an image, so it has to be between 0 and 1. And this is how we do run the attack. So this test function, what it does is, it goes through considering a single specific value of epsilon, so the noise value, the noise amount. What it does is, it tests the image with respect to the ground truth. So we do have access with this particular kind of attack, we do have access to the original training and test data, in particular the test data, meaning that we do know what is the actual target of each single image. And for all of those that the model is correct about, because if the model is already wrong about the image, we're not interested in perturbing those images. The model is already wrong, so we don't need to do any of that. But if the model is correct about the image, so it's producing the right prediction, what we do is we run the attack on this particular image. And so we perturb the data using the attack, and then we reclassify using the perturbed model, and so we compare what has happened with the new perturbed image. This is what the test function does. If we do consider an epsilon noise value of 0.05, what it does is just about reducing slightly the performance of the model. You're more than welcome to run it on your own if you want to. But with this value of epsilon, we are reducing the accuracy from 0.98 to 0.94. And at this point, we wonder how tampered the image look like. So if you look at these images, so what you're seeing on top is the expected label and the predicted label. So a 5 has been predicted as a 6, 3 as a 2, 9 as a 8, another 9 as 8, another 9 as a 5. So this is how the effect of the fast gradient sine method has been producing. The interesting thing is that if you look at the image, they do really look genuine. So they don't look tampered at all. So the last part of this notebook is what happens, how much can we scale the noise addition so that the accuracy is going to go worse and worse, but the image is going to look like they've been tampered in the beginning. So moving from 0.5 to 0.3 with different epsilon values, you can see we can go to the plot at the end. We have a very high degradation of the accuracy, starting from 0.9%, 98% to like 10%, with a very high value of noise. However, the more you go into the higher noise addition, the more you can tell the images have been modified. That's the effect. Okay? So, again, the whole idea here is to fool the model, generating examples which are intentionally going to fool the model prediction. And these are the definition of adversarial example. From a privacy and model threats, this is a version of model attack. Let's now talk about something we've been introducing many times now, which is the model inference attack. So the model inference attack is considering a different data set. Ori faces is the name of the data set. And by the way, what I've been doing in these notebooks is like replicating what is reported in the original paper. So I tried to do a PyTorch version of what the paper was, what the original paper from 2015 was reporting. And you will also notice if you read the paper that there will be a bit of mismatching with at the time terminology for deep learning with what we do use some terms in deep learning terminology nowadays. So for example, well, first off, the oral faces data sets, we're going to take this data set. It's hosted somewhere on a Dropbox account I have, and because it was a bit difficult to download, it was like had to archive, use a web archive for an old page, and it's like provided as a torch data set, and this is how the data set looks like. So we have a data set of faces of human faces, so they're all different people. The target of the classification is going to be who's going to be the individual in the picture, because every single picture of these individuals is taken from different angles. So you have the faces of the same people taken from different angles. And the classification problem is who's the people in the picture. That's going to be the gig. Something I mentioned here is, by the way, you should be seeing the exact same faces on your end, and that's because I fixed the random seed, and that's just a gentle reminder for you to always remember to fix random seed whenever you're dealing with data or machine learning. Right, so the paper was talking about two models at target: softmax regression and multi-layer perceptron. So this is one of the things that has been kindly misleading terminology here. Softmax regression is nothing more than a single linear layer with like softmax activation function. This is what I mean by softmax regression. Multi-layer perceptron is a similar model, slightly bigger, but still classic multi-layer perceptron for classification with linear layers. So what we do here, we focus on softmax regression mostly because it's very easy to work with, and also to derive some consideration. But what we're doing here is like training this model. So we train the model and we save it to some checkpoint that you should be having already on your end if you downloaded all the data in the checkpoint folder. So what the model is doing is like running stochastic gradient descent optimizer. This is MLP, by the way, but I was hoping to get some information about the accuracy of this model. Well, we can probably run it. I don't know why. Oh, I probably don't have it printed, so it's certainly pointless. Right. So this was the preparation of everything. Now let's move on to the reconstruction, which is where we lead our attack. So we have a train model, and so imagine that here the deal is we are considering the model to be like an API, a model as a service in which you can query to get some results. And so again, this is like restarting everything with a data set, and it's preparing for the reconstruction attack. So the reconstruction attack works this way. I just want to highlight what is reported in the original paper. So the membership inference phase is taken a label and some parameters, alpha, beta, gamma, and lambda. So what it does is it's essentially initializing some parameters. And for a certain number of times, it is going to work on this original tensor starting from an empty tensor, all zeros. And if we work on the code, probably it's even better than the paper, I believe. This is the MI phase implementation. So we start with the aim tensor, which is what we're hoping to fill in with the sensitive data in the end. We start from zeros, having the same size of the oral phases data set. And we do specify that this tensor requires gradient, because that's the key to run the attack. We do have some parameters, and what we do is we generate the first prediction from the model, like getting the actual tensor out of the model, not the label, but actually the tensor generated by the model. And we see what is the predicted classes. And then we start a new optimization process running during the attack. So what we do is, for a certain number of alpha iterations, we do rerun model prediction, passing in aim tensor, getting the output. If this aim tensor gradient is not none, so we do have something into this tensor, we do zero gradient, because we're running, again, this extra parallel optimization on the client end. And what it does is we modify, we generate this target class based on what the model is being saying is the class, what is the target class of the attack. So this is the class we're interested in. So we're interested in gathering some data about the class of this particular human being. If the dataset was different, imagine we could select, give me all the information about all the unhealthy patients in my database. If that was one of the class of target. So what we do here is we do run an optimization of the original output the model is producing out of this prediction to the target we want to go to. And essentially what we do is implementing a sort of a stochastic gradient descent step in which once we have this gradient, we use this gradient to change the content of this aim tensor, which is acting as a bucket of information we keep on changing during the process. And by the way, this process function here is not going to do much, and this is just normalizing using min-max scaling. This is what it's doing. If you read the paper, they were doing better normalizations, so you were leading to better results. This is just to tell you why the quality of the prediction we're gathering at the end is not going to be as good as the paper, because we're not normalizing much the data, but it's like just to prove the point. So essentially what it does is you do this internal optimization on the client end for a certain number of iterations, and if you have a loss which is unacceptable beyond a certain threshold, you stop the iteration and that's it. And this is what you're generating afterwards. So if we're trying to run this attack on the softmax regression, which is, by the way, the pre-trained model we've been training, selecting different classes from the dataset, this is what we generate. We start from empty tensor, we lead to this image. We start from an empty tensor, class 1, we lead to this image. And again, start class number 2 is the target, empty tensor, different person. Different class, empty tensor, different person. So this is like gathering, and of course, again, the quality of the reconstructed images is not as good as in the paper, because we're not normalizing. They apply different normalizations. I just did like min-max normalization. You can do PCA. They do, I think, PCA normalization or something. But again, it's not the point. It's just to prove you that you can steal information from trained model. And the caveat of all this approach is this model is actually quite easy to steal from because it's an overfitting model. So based on that one, you're essentially using this model producing a tensor when running the attack, so you have lots of information there. But these are just examples. Right. And this is the final result. So in this exercise here, it is telling you to try with another model, multi-layer perceptron, and these are some of the examples you can run as well. But similarly, the model is slightly more, it does require slightly more number of iterations to run the attack, because the model is not that simple, has just 3 layers more than just a single layer softmax regression. But still, you can gather pretty much good results. So now you know already what's the gig here. So I just want to skip directly to the final result. Meaning I want to reconstruct now the model after training using Opacus. And I just want to highlight how easy it is to use Opacus. And hopefully now we'll be able to understand some of the meaning of the parameters you have to provide. Well, first off, I'm not going to go much into the details, just want to highlight 2 important things. First off, what does Opacus provides is a validator. And this is very useful because whenever you have a model, you can validate your model against differentially private requirement. What's the deal here there? Sometimes some of the layers internal to the model are not as easy to differentially to make them differentially private. One classical example: dropout or batch normalization. They do have internal parameters that you cannot control, and so it's not possible. If the model has some of those layers, Opacus is going to validate the model and say, look, I try to do my best, but I can't do really everything. So you have a warning there. The second thing very useful Opacus provides is called privacy engine. We're going to use a specific function from the privacy engine called make private with epsilon. And to this function, what we do provide is an epsilon value, which is privacy budget. we have a delta value, which is the delta budget from an approximate differential privacy method. And then we say, what is the maximum gradient norm we want in the distance for sensibility, and how many epochs we want to run the training. Different from the original training model, we've been increasing the number of epochs by 100. So instead of running the training for 100 epochs, we run it for 200. And the reason for that is now the computation is going to take much more iterations in order to come up with some interesting results. So I'm not going to run anything, but what I want to highlight here is once we run, when we use this privacy engine, we have to provide the model we want, the optimizer we want, and the data loader we want, in addition to the other parameters for differential privacy. And what Opacus is returning is a new version of the model, differentially private, a new version of the optimizer, differentially private, and a new version of the data loader, differentially private. The differentially privacy in the data loader is how you essentially gather the data from the loader, so the random picking of the sample, but at the same time, if you want to run some of the differentially private mechanism to the samples rather than the gradient, depending on the loss function you're using. Similar things we've been discussing earlier. You set up your engine, and then the very useful thing is you can perfectly reuse the same function, the same train function I've been using before to train my PyTorch model. I don't have to change anything. You just change the wrapping around, so differential privacy via Opacus is going to be a wrapper around the different deep learning components you already had, and then you use the same function again, and everything works. So you don't have to deal much with the gory details. It's like you just wrap everything around, you set the parameters, and it goes. And what you get in the end is a fully differentially private train network. And so with this network, what you try to run the attack, whatever you're getting is this. There's nothing there you can extract from, because the model has been trained using differential privacy. Does that make sense? Ultimately, like half an hour before the end. And this is one of the main results we wanted to gather today. So the first part, with all the details of why k-anonymity is wrong, and why differential privacy is similarly important, and how this ties into machine learning, this is one demonstration of how effective it can be when it is brought into the deep learning training. Of course you can. I just want to check whether I have a piece of information at the end. That's, I don't know. Yeah, go ahead. Haha. Well, embeddings are vector data anyway. So it's, again, nothing going to change much, because at the end of the day, machine learning and deep learning are always crunching numbers, no matter what is the data format. So you're dealing with images, it's numbers. You're dealing with languages, it's numbers. So it's always a matter. So this is a very good question, and thank you very much for that. It's something that we probably oversee most of the time, because deep learning has brought into machine learning something absolutely powerful. You can do end-to-end things. You don't have to work on features before. You can have the model to figure it out. And so you might be tempted of thinking that you can work on whatever kind of data format, and ultimately it's true. But you can do that up to the point that you can convert that piece of information into numbers. If you can't, there's much you can do with deep learning anyway. So it's going to be numbers. Very long and convoluted way to reply. Yes. Yeah, that's good. That's a very good point. Well, categorical values can be dealt in a similar way you would deal with deep learning, because deep learning cannot process categories, or as in you normally create a sort of embedding to go into something those categories from. But otherwise, I guess what I'd say, like off the top of my head, would be I haven't thought this through, so I might be wrong there, but you can treat categorical data as numerical data anyway, so you can perturb them to be less meaningful in the sense of, instead of being like 0, 1, they could be like 1.5 or 0.5, something like that. But still, it's about gathering noisy version of data that do make sense in a way. But I do like to take some time to think about it. It could be probably wrong. Yes. That's a very good point. Yes, that makes sense. That makes sense to me. So what you're saying is you're converting your categories into queries of counting, and so you can. It's exactly the same thing. So you're adding noise to the actual data, similar to what you would do with counting queries. Same thing. You're right. Totally right. That makes sense to me. But again, it's an open question for me. I should probably look into that. But this answer makes sense to me. And thank you very much for the questions, by the way. Yes, go ahead. Mm-hmm. Yes. Same. Yes. Sure. You can, until you have access to the weights. What we're doing here is black box attack. So we don't have access to the model internals, we just have access to the predictions. And so we're tampering the predictions so that we can extract some pieces of information. If you have different kind of access to the model, you have plenty of ways you can deal with the model. Yes. So one technique could be to apply differentially private weight strategy to prevent that. But normally, if you can prevent it at the origin rather than at the end, so like if you train the model with differential privacy rather than applying differentially private inference, is generally better. If you can't train a model because, for example, it's a model pre-trained, and then, I don't know, you fine-tune it and then you want to do something else, you can similarly apply differentially private mechanism to the weights. Yes, totally. This is what it does. It does it a certain number of times in order to have the model converging, but it's what it does. Something I was hoping to showcase, but it's not there. But if you can run it on your end, it would be interesting. Would be to see how accurate the model is. So if we load the pre-trained model and you try to run accuracy on the test data, you will be seeing that the accuracy, the final accuracy, is not going to be as good as the original model, but it's acceptable. So again, it's a trade-off between utility and privacy. Was there any other question? Okay. So, yes. Thank you. Okay, so Opacus belongs to the PyTorch family. TensorFlow has another one, and it's it's very fine. And actually, it's very, very good for you to say that, because Opacus is actually starting from a previous project, what's called TensorFlow TensorFlow DP package, and it's the equivalent for TensorFlow. So you do have options. I just chose Opacus because I prefer PyTorch over TensorFlow, but that's my gig. It can be similarly valid. So you can do this same framework regardless of the framework, the deep learning framework underneath. It's an extra package. It's an official PyTorch supported project, but you install it from pip or CondaForge as a package, and then you start using it. If you look at the environment I had, it's literally an entry around here. So in this case, it's pip installed for having the environment resolving quickly, but it's also available in CondaForge. And I skipped the notebook about introducing PyTorch or Opacus, but there is a notebook introducing the Opacus specifically. So if you're interested, you have a link here, and this is Opacus website, and this is how you install it. And after that, you start using it in using models. As simple as that. Also has a very useful thing in the documentation, still taken from. You have some articles here, very useful to know more for the readings. In the documentation, there is a particular utility here, which is called, there was a utility function. I don't remember where that is now. It's probably somewhere in my endless list of tabs. But it was about to try to calculate. It's an utility function that you can use in order to estimate the parameters for privacy budget and other sensitivity parameters. You can use applying a similar kind of approach or the one we've been seeing when we were trying to find an upper bound for the summation queries for sensitivity. So you have, in addition to code to integrate into PyTorch, you also have utility things you can use to work on your actual data. Can it be this one? No. I will find a reference and put it in the notebooks right now. What? That's a good question. Thing is, as far as I know, no. At least not that I'm aware of, but I will certainly have a look. It does make sense to have it, although I think it's more complicated, and because this is something. Well, there is something, and to be honest, there is indeed some effort in that particular case. So I want to amend my answer and say yes or no. It's not an astounding no, it's a yes or no. And also an opportunity for me to shout out to a very nice community I've been contributing to as well. It's called OpenMind. OpenMind provides you tools and also some courses and materials. They actually reference it in materials. I was actually going to say that. But what I really want to say here in answer to your question without talking about many things at the same time is they do work on a very interesting project. It's called SIFT or PySIFT, which is data science with privacy budgets. So it's a sort of a framework that you can use to run any, not just machine learning, but that's why it's an interesting project because in the beginning was mostly about machine learning. Now they like shifting the focus to a more general, broader audience. So like talking PET, privacy enhancing technologies at large, not just machine learning things. So that's why I'm mentioning this, but not going much into the details. Nonetheless, what they're doing is a data science platform in which you can query databases, and from the backend side, you can set up a privacy budget, and you can return. You can have differentially private mechanism answering your queries automatically for you, and the whole thing is based on a distributed architectures of Docker containers. So you can be either private and distributed in the multiple agents communication. It's a very complex architecture that deserves tutorials by itself. There is some effort into bringing differentially private mechanism into other libraries. Pipeline DP, for example, is using Apache Beam to set up pipelines for differential privacy. And there was this PyDP project I started contributing in the beginning. This PyDP is trying to bring differential privacy library for scikit-learn models. So we have naive Bayes and other examples here. The real difficulty in dealing with scikit-learn in the way it is designed is whenever you want to run differential privacy on the parameters of the model, you cannot do that as easily because scikit-learn is very difficult to access parameters during the training. So most of the training in scikit-learn is done with external libraries. So and C implemented. So even if you run the training with scikit-learn, it's very difficult. You have no access to the parameters. So you have no way in which you can integrate in how the training goes for most of the majority of the models. Naive Bayes is a specific case you can do that because if, for example, logistic regression, which is a simple one, we had to reinvent the wheel and re-implement everything from scratch exactly for this reason. Because we couldn't integrate into how the training works. It was also didactic because we wanted to explain things a little bit, but the technical reason for that was like it was difficult to deal with. So that's at least to the best of my knowledge. That's why to date it's not that easy to integrate this kind of technologies into scikit-learn. Nonetheless, most of the research to model threats and model vulnerabilities focus on deep networks as well. So it's also another reason why most of the effort has been spent there. But it's a very fair question, to be honest. All right. So the very last part is asking a slightly different question and asks, why don't we allow AI or machine learning, deep learning, whatever that is, without moving data from their silos? And this is a way to introduce federated learning. Federated learning is another piece in this big framework we're talking today. Federated learning, believe it or not, started from a completely different scenario in mind, but has been recently shifted and repurposed, if you want, into the framework of privacy preserving technology. So the whole idea of federated learning in the beginning was to leverage on the fact that it was designed by Google. It was based on the fact that when we are considering mobile devices, they do have processing capabilities nowadays. So we can have access, potentially, to distributed computation capabilities in our devices. And the whole idea is to running some machine learning training or predictions, whatever, on your own mobile devices, and so on your own data, without having neither the model or the data leave the device. So the whole idea of federated learning was, why don't we set up a distributed approach to train a model, a global model, starting from the local distributed models from each devices. And so the idea is we need to find a way so that the models distributed in every single mobile devices can be trained on the local data, so data that lives on the phone, but they can also benefit from the data of other clients in this federated framework without accessing data directly. And so how the whole thing works is this way. So you have your single client trained on the local data, and once the data is being trained, when the model is being trained, the gradient of this model is being put into the network. And so is the case for all the single devices. There is a global network in the cloud gathering all the possible gradients from all the possible clients, and the server, the global central server, is going to acquire all the gradients, finding a strategy to combine this. Normally is an average. So you generate a new gradient, which is the average of all the possible gradients you've been considering. And so indirectly, you've been creating a new gradient, which is able to incorporate all the indirect input you got from data from all the clients. And this new average gradient is being distributed back to all the clients, so that the new client, the next generation of training data, is going to start from a local model on local data, which incorporates gradient from all the other clients in this framework. Does that make sense? Is that more or less clear? So the multiple clients are sharing information about the other clients indirectly via gradient. So they're not having any access to any local data from other clients. Only the average gradient. So not even the gradients between models, only the average gradients. The problem is that we've been seeing that these models can be used. If we do have access to the gradients, we can use these gradients to be as a source of attack. So another possible direction to take into consideration is, yes, we can have federated learning, but federated learning by itself cannot be enough to guarantee privacy requirements. So what we can do is like applying encryption to the gradient. And how the encryption is going to work. We cannot apply any kind of encryption. We can apply, but we need to apply specific kind of encryption. Why we need that? Because essentially, you have to think that every single gradient from every single client can be encrypted, and that's fine. But, well, first off, this encryption has to happen with, if you're familiar with how asymmetrical encryption works, you essentially have a public and a private key. So the private key is going to be on hold by the global model, so the one having the full central control. And every single client can have the public key. So every single client can produce their gradients, and they can encrypt these gradients using the public key provided by the global server. The problem is that whenever it comes to average the gradients, you have to make sure that the kind of encryption you've been using is a specific kind of encryption so that it's still reliable based on arithmetic operations. In other words, if I do sum up the encrypted values of the encrypted gradients, and I do average the encrypted gradients, the decrypted version of the encrypted average I get is the original one, is the one unencrypted, is the correct one. And this kind of encryption is called homomorphic encryption. It's a specific family of techniques which is particularly useful because it could be, it's supporting arithmetic operations on encrypted data. Exactly what we need to run machine learning models on encrypted data. Does that make sense? I think for you it makes a lot of sense because if you might have been seeing homomorphic encryption security already, right? So this is exactly what I said in the very beginning, and I told you there was something that would make sense in the very end, as in privacy and security are two different things, but they might collide and cross ways at some point. And this is one option. So this is further learning to retain privacy on the data, merging with homomorphic encryption, which is a very specific kind of encryption in which you can train your model on encrypted data. So whatever operation is going to do on the encrypted data is going to make sense. It's not going to be gibberish. That's what it is. Right. So in the interest of time, also because I'm particularly exhausted, 4 hours tutorial is quite a day. I just want to tell you what is the further learning bit. Well, the intro to further learning is talking exactly to what I've been talking to, and the homomorphic encryption is provide you a concrete example of running this into a very simple scenario, but is going to prove you the point of having partially homomorphic encrypted data within machine learning models. And since it's going to be like security related, I think we're going to have a class of Alice and a class of Bob, because always Bob and Alice are talking into security problems. And so we're having them to talk, and they do exchange keys, and ultimately what they do is, so Bob is going to be the one computing score on encrypted data, and Alice is the one holding the keys. So Alice is generating the key pair, distributing the key to multiple clients, and these clients are essentially running their model on encrypted data, going back to Alice. Alice has gathered the encrypted data, decrypted it, and it makes sense. This is what happens in this notebook. This is just like details of the implementation. The third notebook is to introduce you to what I already talked about OpenMind efforts into privacy and non-stick technologies and access to. They have an actual course of free courses if you're interested. So far, they're featuring Introduction to Remote Data Science, Privacy Opportunity, a Foundation of Private Computation, and I think they do have a pretty consistent way of updating the material, as well as tutorials included there. And last but not least, there is a much more concrete example of using PyTorch and the Flower framework. Flower is a very interesting project I discovered personally not much long ago, and is a deep learning independent kind of a project supporting PyTorch in this notebook, but it also has integration with other frameworks like TensorFlow, for example. And this particular notebook is an adaptation version of workshop material shared after the latest Flower Dev Summit. You can find information here, and it demonstrates how you can run. You can have an API with further learning. What it does not support yet, Flower, is the homomorphic encryption support. So from Flower, you can have full support of everything needed for having a distributed computation of our clients and servers using further learning, specifically for the sake of machine learning or deep learning, to be more precise. But it's on the roadmap of integrating as well deep homomorphic encryption and differential privacy. And I would not be surprised if those were coming from integrating with existing tools like Package, for example. Just going through very quickly the content of the notebooks. What it does here is using MNIST and is simulating, this is the particularly interesting feature of Flower. What it does is simulating a further learning to train on MNIST dataset. In particular, you have a certain number of clients, 10 in this example, and you partition the data into 10 different clients so that you assume that every single client has their own version of the data. And something I haven't mentioned in details, but I'm telling you right now, is normally you figure out further learning into a horizontal way, in which you essentially split the data into slices by samples. But another way you can split your data is also vertical, and it's called vertical further learning. And a classical example is, I have a data set of medical imaging, you, another client, has a data set of clinical data, and a third hospital in the framework has access to the labels for the same set of samples. So the deal for further learning to actually work, and this is a big constraint, either these being horizontal or vertical, is in the case of horizontal further learning, we are actually slicing up on the zero-axis in terms of NumPy axis dimension. So we're slicing up on samples, assuming that every single partition has the same set of features. So we're slicing on one dimension, but the other dimension is fixed. If we're doing vertical further learning, we're slicing upon the feature side, but we're assuming the set of samples is the same. Otherwise, nothing is going to work. So you have to fix one dimension and you slice on the other direction. And I think that's it. I would stop here, and I would get any question you might have about this part, or whichever part you want. And thank you very much for bearing with me till the very end. You have any question? All right. Well, thank you. Now, I need to know how to stop sharing and recording my screen. I throw it away. At that point, it will stop. Just because in the interest of privacy, I definitely don't want to... There you go. I definitely don't want... Okay. I'm going to save it. I hope that was supposed to be. Recording is unlimited to 2 hours. I'm talking for 4 hours. What's going on here? I hope this is going to go. Anyway. Oh, okay. So, the very last thing I'm going to say is, you know the repository now. If you find anything wrong or something you think it could be improved, please let me know. Pop in an issue. I will certainly have a look. Thank you so very much. Sci-fi 2123, and I also have a poster. This is going to be something particularly funny. But if you happen to come around a poster session, we're happy to speak with you.